Picture, for a moment, a canvas of near-total blackness. It is not the empty black of a moonless night, but a profound, seething darkness, the universe in its raw infancy. There are no stars to cast light, no planets to host life. Not even the familiar atoms that make up our world have settled into their stable forms. In this primordial chaos, in the wake of the Big Bang's unimaginable release of energy, the cosmos was a simmering soup of fundamental particles, a place where existence itself was being forged in the most extreme conditions imaginable. It is within this seemingly inhospitable furnace, in the first fleeting moments of time, that one of the greatest and most profound mysteries of our origins was quietly being solved. Before anything we would recognize as a structure could form, before the grand cosmic architecture of galaxies and nebulae could even be conceived, the universe had to perform its first and most crucial act of chemistry. It had to build something from almost nothing. It had to create the universe's first complex molecules. What were these pioneering molecular structures? What strange and elegant compounds emerged from the swirling plasma of the early cosmos to lay the very bedrock upon which all future complexity would be built? This is not merely a question of chemistry, it is a question of our own deepest ancestry. The answers are etched into the fabric of reality, a faint chemical signature left behind from a time so distant it defies human comprehension. For decades, scientists have peered back through billions of years, using powerful telescopes and sophisticated theoretical models to reconstruct this lost epoch, piecing together a story written not in stone, but in the spectral lines of ancient light and the residual echoes of creation itself. They have proposed a breathtaking array of possibilities, each theory a window into a different version of our universe's first tentative steps toward order and ultimately life. In this journey, we will explore 30 of the most fascinating and compelling theories about these foundational molecules. We will venture into a realm where hydrogen and helium, the universe's only abundant elements at the time, had to perform chemical miracles. We will investigate how, in the crushing densities of the first protogalactic clouds or in the violent surroundings of the very first dying stars, the first fragile bonds between atoms were formed. This is a story of cosmic alchemy, of how the simplest building blocks assembled into the precursors of everything from the water in our oceans to the DNA in our cells. So join us as we unravel the secrets of our cosmic cradle, tracing the chemical lineage of the universe back to its very first and most important creations. Our journey into the cosmos's first chemistry begins not in the depths of space, but in a landmark laboratory experiment conducted in the 1950s. Two scientists, Stanley Miller and Miller-Urey, sought to recreate the conditions of a young planet Earth inside a series of glass flasks and tubes. They filled their apparatus with what they believed were the planet's early atmospheric gases: water vapor, methane, ammonia, and hydrogen, and then subjected this mixture to continuous electrical sparks, simulating the violent lightning storms of a primordial world. After just a single week, the results were staggering. The once clear water had turned a murky, reddish color, and upon analysis it was teeming with organic compounds, including several different types of amino acids. These are the very molecules that link together in vast chains to form proteins, the workhorse molecules of life as we know it. This single experiment, now famously known as the Miller-Urey experiment, provided a powerful and elegant proof of concept. It demonstrated that the fundamental building blocks of life could arise spontaneously from simple, abundant ingredients and a readily available source of energy. This concept of a primordial soup, a rich broth of prebiotic chemicals simmering on the surface of an early world, became the dominant theory for decades. It suggests that on countless young planets and moons throughout the galaxy, similar processes were likely at work. Ultraviolet radiation from a young star, the geothermal heat from a volcanic vent, or the shockwave from a meteorite impact could all serve as the catalyst, providing the necessary jolt of energy to transform simple molecules into more complex ones. The implication is profound and universal. The universe, it seems, has a built-in bias for chemistry, a tendency to move from simplicity toward complexity whenever the conditions are even remotely suitable. The amino acids formed in Miller and Urey's flasks were not just evidence for life's potential on Earth. They were a template for a process that could be happening on innumerable worlds right now. However, while the primordial soup theory provides a compelling narrative for the formation of life's building blocks on planetary surfaces, it does not directly address the very first molecules that formed in the universe itself, long before the first planets ever coalesced. This is where the theory expands beyond our own world. Astronomers have since detected the spectral signatures of simple amino acids like glycine in molecular clouds in deep space, within the vast, dark nebulae where new stars are born. This discovery suggests that the chemical pathways demonstrated by Miller and Urey are not confined to planets. They may, in fact, be a universal process occurring in the icy mantles of dust grains floating in the interstellar void, energized by cosmic radiation rather than lightning. So, the first complex molecules in the universe may not have been forged in a planetary soup at all, but in the cold, dark, and immense chemical laboratories of interstellar space, seeding young solar systems with the essential ingredients for life even before their planets finished forming. But if the formation of amino acids in space was a revelation, the discovery that followed was nothing short of a cosmic sweet surprise. Far from the imagined primordial soups of early planets, astronomers began to detect the unmistakable chemical signature of sugar, not table sugar, but a fundamental variety known as glycolaldehyde. This simple two-carbon sugar molecule is far more than a celestial treat. It is a direct and crucial precursor to ribonucleic acid, or RNA, which many scientists believe was the first molecule capable of self-replication and thus a cornerstone for the very origins of life. The fact that this compound was found not in a sheltered laboratory or on a balmy planet, but within the vast, turbulent, and incredibly harsh environment of a giant molecular cloud known as Sagittarius B2, near the center of our own galaxy, completely rewrites our understanding of where life's essential chemistry can begin. This discovery forces us to confront a stunning reality. The conditions within these interstellar clouds are among the most hostile imaginable. Temperatures hover just a few degrees above absolute zero, the point where all molecular motion nearly ceases. There is virtually no protection from a constant bombardment of intense cosmic radiation, and the density of the gas is 1,000,000 times thinner than the best vacuum we can create in laboratories on Earth. In such an environment, the chance encounters between individual atoms are exceedingly rare, and the energy required to forge them into a stable molecular bond seems almost impossible to muster. Yet, the evidence from our most powerful radio telescopes is unequivocal. Glycolaldehyde is not only present in these clouds, it appears to form there in significant quantities. So how does this delicate sugar molecule assemble itself in what amounts to a deep space freezer under constant radiation assault? The answer lies on the surface of the most unassuming and abundant objects in the cosmos, interstellar dust grains. These microscopic particles, primarily composed of silicates and carbon, are the soot of the universe, forged in the fiery deaths of ancient stars and scattered across galactic space. In the frigid depths of a molecular cloud, these tiny grains become icy havens. Atoms and simple molecules like carbon monoxide and water vapor slowly drift through the void, and upon striking a dust grain, lose their energy and become stuck to its surface in a layer of frost. This icy mantle acts as a miniature chemical laboratory, a two-dimensional arena where these simple ingredients are held in close proximity. Then, when a stray packet of ultraviolet radiation or a cosmic ray strikes the grain, It provides the precise jolt of energy needed to break existing chemical bonds and allow new, more complex ones to form right there on the grain's surface. It is through this slow, patient, and cold chemistry that glycolaldehyde is thought to be built, one molecular addition at a time. The implications of this process are staggering in their scope. It means that the fundamental sugars necessary for constructing RNA, and by extension the first genetic code of any potential life form, are not a happy accident unique to Earth. They are a universal byproduct of star formation and galactic evolution. Every time a new generation of stars and planets begins to coalesce from a giant molecular cloud like Sagittarius B2, that nascent planetary system is already preloaded with these essential biological ingredients. The comets and asteroids that will later bombard young worlds are not just balls of ice and rock. They are delivery vehicles carrying within them a payload of pre-formed, complex organic molecules, including the very sugars that can kickstart the journey toward life. This theory suggests that the universe, in its cold, dark, and seemingly empty spaces, is inherently productive, quietly and persistently manufacturing the seeds of complexity long before any star ignites or any planet forms, offering a profoundly optimistic view of life's potential prevalence across the cosmos. Yet, the universe's molecular toolkit was not limited to sugars. In fact, one of the most abundant families of complex molecules in the cosmos is something we might, on Earth, associate more with a smoky barbecue or a car's exhaust pipe. These are the polycyclic aromatic hydrocarbons, or PAH. Picture, if you will, the soot rising from a candle flame. At a microscopic level, that soot is composed of flat, sheet-like molecules made of carbon and hydrogen atoms arranged in interlocking hexagonal rings, much like a microscopic honeycomb or a panel of chicken wire. This is the fundamental structure of a PAH, and this seemingly mundane terrestrial substance is astonishingly one of the most common forms of organic matter in the entire universe. The infrared eyes of our most powerful space telescopes have detected the unmistakable signature of these molecules almost everywhere we look, in the vast clouds of interstellar space, in the swirling disks around young stars, and even in the light from other distant galaxies. They are, in effect, the cosmic soot that permeates the fabric of the cosmos. Their prevalence points to a fascinating and violent origin story. PAHs are not forged in the gentle, cold chemistry of interstellar dust grains like some other molecules. Instead, they are the robust survivors of stellar infernos. They are believed to form in the carbon-rich atmospheres of aging, red giant stars, where temperatures are just right for carbon atoms to link up into these sturdy, ringed structures. When these stars eventually shed their outer layers into space, or in the catastrophic explosions of supernova, trillions upon trillions of these PAH molecules are ejected out into the galactic environment. Their flat, sturdy shape makes them remarkably resilient, allowing them to withstand the intense radiation fields of interstellar space that would easily tear more fragile molecules apart. This durability is key to their cosmic success. They are the hardy pioneers, the long-haul truckers of organic chemistry, carrying the essential element of carbon across the vast distances between the stars. This abundance of carbon-rich material is not just a curiosity. It fundamentally shapes the chemical potential of new planetary systems. When a new star and its surrounding protoplanetary disk begin to coalesce from a cloud that is rich in these PAHs, these molecules become a primary ingredient in the construction of new worlds. They are thought to coat the surfaces of dust grains and become incorporated into the asteroids and comets that will later agglomerate into planets. In this way, a young, barren planet like the early Earth would have been seeded from the very beginning with a massive, pre-delivered inventory of complex carbon-based molecules. This is a crucial distinction. Unlike the Miller-Urey experiment, where amino acids had to be built from scratch from simple gases, a world enriched with PAHs already has a head start. It doesn't need to invent complex carbon chemistry. It merely needs to rearrange and build upon the sophisticated molecular Lego bricks that the universe has already provided in staggering abundance. The role of these molecules may have extended far beyond just being a source of raw carbon. Their unique physical and chemical properties make them incredibly versatile players in the story of life's origins. Their flat, wide structure means they have a tremendous surface area, and in the chaotic environment of a young planet, they could have acted as primitive catalysts, providing a stable platform upon which other, simpler molecules could gather and react with one another to form even more complex structures, perhaps even the first genetic molecules. Some laboratory experiments have even shown that when exposed to water and radiation, PAHs can spontaneously stack on top of one another, forming rudimentary structures that bear a striking resemblance to the way base pairs stack within the DNA double helix. This hints at a breathtaking possibility that the very architecture of life's information-storing molecule may have been prefigured by the physical behavior of these abundant cosmic compounds. They were not just inert ingredients, they may have been active participants, their inherent chemistry subtly guiding the universe toward greater complexity and ultimately toward us. But the universe's recipe for life's essential sugars has another, even more elegant pathway, one that seems almost too simple to be true. This is the foremost reaction, a chemical process so fundamental that it can spontaneously generate a family of sugars, including the all-important ribose, from a starting ingredient as basic as formaldehyde. Imagine a chain reaction of molecular connections, a kind of domino effect in the chemical world. It begins when two molecules of formaldehyde, a simple compound of carbon, hydrogen, and oxygen that is astonishingly common throughout the galaxy, linked together. With just a slight nudge from a mineral catalyst or a trace of calcium, this initial pair encourages another formaldehyde to join, and then another, causing the chain to grow and spontaneously branch into a complex mixture of different sugar molecules. In a laboratory setting, this reaction is a sight to behold, often starting with a clear solution that gradually turns a yellowish hue as it becomes a veritable soup of carbohydrates, all emerging from the most primitive of ingredients. The profound significance of this reaction lies squarely in one of its many products, ribose. This specific 5-carbon sugar is the literal backbone of RNA, or ribonucleic acid. In every living cell on Earth, RNA performs a dazzling array of vital functions, acting as a messenger carrying instructions from DNA and as a catalyst for essential biochemical reactions. Many scientists who study the origins of life posit that RNA, or a molecule very much like it, was the very first self-replicating system on our planet, a molecule capable of both storing genetic information and speeding up its own reproduction. This RNA world hypothesis places ribose at the absolute center of the story of life's dawn. Without a stable and abundant supply of this sugar, the entire elegant architecture of the first genetic systems could never have been built. The foremost reaction, therefore, represents a potentially universal and incredibly efficient factory for producing this critical molecular component from scratch. The great cosmic question, then, is where such a delicate and specific reaction could have found a stable home to proceed. The answer points us toward the bustling construction sites of our own solar system, the surfaces of early asteroids and the turbulent atmospheres of protoplanets. Consider an asteroid in the early solar system, a rugged worldlet composed of rock and ice. Its surface, constantly bombarded by ultraviolet light from the young sun, would have been a patchwork of ices, including a significant amount of formaldehyde ice. Embedded within the asteroid's rocky matrix are also various minerals. Laboratory experiments have shown that certain common minerals, like calcium carbonate or silicate clays, can act as powerful catalysts for the foremost reaction. These mineral surfaces provide an ideal platform, holding the simple formaldehyde molecules in place and orienting them in just the right way to dramatically increase the likelihood that they will link up into the more complex sugar chains, effectively turning a random asteroid into a microscopic sugar production facility. Alternatively, we can look to the skies of a young, still-forming planet. The early Earth likely had an atmosphere rich in carbon dioxide, water vapor, and methane, and through the action of ultraviolet light and electrical discharges in lightning storms, formaldehyde would have been readily produced, raining down continuously onto the planet's surface. But in the atmosphere itself, suspended dust grains and water droplets could have served as tiny chemical reactors. A mineral dust particle coated with a thin film of water and enriched with formaldehyde, floating high in the skies of a primordial world, would present the perfect confined environment for the foremost reaction to proceed. The energy from the sun would drive the reaction forward, and the protective shell of the water droplet could shield the fragile sugar products from breaking down too quickly. This process would have gently showered the young planet's oceans and land masses with a steady, rain-like infusion of probiotic sugars, constantly replenishing the planetary inventory with the essential building blocks for RNA. However, the foremost reaction presents a fascinating paradox that highlights the delicate balance required for life's chemistry. While it is brilliantly efficient at creating a wide variety of sugars, it is notoriously non-selective. It produces a chaotic mixture of many different sugar molecules, and ribose is just one among dozens. Even more problematic, ribose is chemically quite fragile, especially in the conditions we imagine on the early Earth. It tends to break down quickly unless it is stabilized by being incorporated into a larger molecule like RNA. So how did nature select for this one specific, somewhat unstable sugar from a chaotic chemical cocktail? This is where the mineral catalysts on asteroids or in atmospheric droplets may have played a second, even more crucial role. Certain types of clay minerals have surfaces with very specific atomic geometries. It's possible that these surfaces not only catalyzed the foremost reaction, but also acted as a molecular filter, preferentially absorbing and protecting the ribose molecules from destruction while allowing other, less useful sugars to degrade. This would mean that the very rocks and dust grains of the early solar system were not just passive platforms for chemistry, but active participants in a grand cosmic selection process, subtly guiding the universe's chemical output toward the specific structures that would one day become the foundation of life itself. While the cosmos was busy brewing sugars in the void and scattering soot across the galaxy, a radically different kind of chemical laboratory was coming to life in the profound darkness at the bottom of an early Earth ocean. Here, completely cut off from the sunlight and turbulence of the surface world, another theory suggests that life's most critical chemistry was being driven not by stellar radiation, but by the very geology of the planet itself. This is the world of deep-sea hydrothermal vents, specifically a type known as alkaline hydrothermal vents. These are not the scorching, acidic black smokers that spew superheated, mineral-laden water, but gentler, more enduring structures that form when seawater reacts with the planet's mantle rock. They build up porous, chimney-like formations that are honeycombed with microscopic compartments, and within this labyrinth of rock, a continuous and powerful chemical engine was running for millions of years. The magic of these vents lies in a simple yet profound natural gradient. The water spewing from these vents is warm, highly alkaline, meaning it is the opposite of acidic and rich in dissolved hydrogen gas. This vent fluid is dramatically different from the cold, slightly acidic and mineral-rich seawater that surrounds it. Where these two fluids meet, right within the porous mineral walls of the vent structure, exists a fundamental disequilibrium. It is a state of persistent chemical tension, a gentle but constant push and pull of protons and electrons across the thin mineral membranes that separate the vent's interior from the ocean. This gradient is not unlike the electrical potential that exists across a battery's terminals. and it is this very same kind of natural energy that could have been harnessed to power the formation of the first complex organic molecules. Within these microscopic rocky pores, the stage was set for a new kind of synthesis. The vent fluid provides an abundant supply of hydrogen gas and other simple molecules like carbon dioxide, which dissolves readily in the ocean water. The mineral walls, often composed of iron-sulfur compounds, act as powerful natural catalysts. Critically, the thin barriers between the different chemical environments create a kind of molecular trap. As hydrogen and carbon dioxide diffuse through these pores, the mineral catalysts, energized by the natural proton gradient, encourage them to react. Laboratory experiments have beautifully demonstrated that under conditions mimicking these vents, these simple ingredients can be coaxed into forming acetate, a 2-carbon molecule that sits at the very heart of metabolism in every living cell. From this foundational acetate, a cascade of further reactions becomes possible, building up more complex chains that are the direct precursors to the fatty acids that make up cell membranes and the amino acids that build proteins. This theory offers an elegant solution to one of the trickiest problems in the origin of life, the formation of the first cell-like compartments. All life as we know it requires a boundary, a membrane to separate its inner workings from the outside world and to concentrate the chemicals necessary for reactions. The same mineral structures that are catalyzing these reactions also provide a ready-made solution. The microscopic pores in the vent rock are, in effect, the universe's first test tubes. Each tiny cavity naturally confines and concentrates the newly formed organic molecules, preventing them from simply diffusing away into the vastness of the ocean. These rocky compartments provide a sheltered nursery where chains of chemical activity can become established and grow in complexity, all while being continuously fed by the vent's steady flow of energy and raw materials. What makes the alkaline vent theory so compelling is its self-contained and protected nature. On the violent surface of the early Earth, constantly bombarded by ultraviolet radiation and asteroid impacts, delicate chemical experiments would have been repeatedly shattered. But at the bottom of the ocean, nestled within the mineral matrix of a hydrothermal vent, these first tentative steps toward biochemistry were cradled in a stable, energy-rich, and deeply protected environment. The vent provides a continuous source of chemical energy for potentially millions of years, far more reliable and durable than any lightning strike or UV flash. It simultaneously solves the problems of energy, catalysis, and compartmentalization in one integrated system. This paints a picture of life not as a lucky accident in a random puddle, but as an almost inevitable outcome of planetary geochemistry, a natural consequence of a water-rich world with a hot, active core. And if this is true for Earth, then any ocean world with a similar geological heartbeat, like Jupiter's moon Europa or Saturn's moon Enceladus with their vast subsurface seas, could be hosting the very same slow, patient, and persistent chemical processes in their own lightless depths right now. But just as we find ourselves drawn to the idea of life emerging from the protected, rocky nurseries of deep-sea vents, we must also cast our gaze upward to the dark expanse above. What if the most crucial ingredients for life did not originate on our planet at all? What if Earth was simply the fertile soil that received a precious delivery of pre-formed molecular seeds from the cosmos? This compelling idea is known as panspermia, a hypothesis that suggests the building blocks of life, or perhaps even life itself in a dormant state, are not exclusive to any one world but are instead common throughout the galaxy, hitchhiking between planetary systems on board asteroids, comets, and meteorites. It transforms our planet from a solitary chemical laboratory into a connected participant in a vast interstellar ecosystem, one where life's raw materials are traded across the void on celestial freighters. The concept itself is ancient in its philosophical roots, but it gained scientific credibility with the discovery that space is far from empty. it is filled with complex organic chemistry. The most powerful evidence for this cosmic delivery system fell to Earth in a brilliant fireball over the town of Murchison, Australia, in 1969. Scientists who rushed to collect the fragments of this carbonaceous chondrite meteorite were astounded by what they found. Inside the dark, primitive rock were not only the expected minerals but also a rich and diverse cocktail of organic compounds. The Murchison meteorite contained over 90 different amino acids, the very same molecules that form the proteins essential for life on our planet. Crucially, many of these amino acids were of a type not commonly found in terrestrial biology, proving they were not contaminants from Earth but were synthesized in space long before our planet even existed. This discovery paints a vivid picture of the early solar system as a dynamic construction zone, bustling with chemical traffic. In the first several hundred million years after the Sun formed, the planetary disk was a chaotic swarm of planetesimals, comets, and asteroids, all constantly colliding and exchanging material. A comet born in the frigid outer reaches of the solar system, carrying a payload of ices laced with complex molecules forged in interstellar clouds, could have its orbit perturbed by the gravity of a giant planet, sending it on a collision course with the inner solar system. When such a body struck the young Earth, it would have done more than just carve a crater. It would have deposited a significant portion of its volatile and organic-rich material directly onto the planet's surface. Simulations suggest that during this period of heavy bombardment, Earth could have received a staggering delivery of organic carbon from these extraterrestrial sources, potentially providing a larger initial inventory of life's building blocks than anything that could have been produced by early Earth's own atmospheric or oceanic chemistry alone. The resilience of these molecular passengers is another key piece of the puzzle. We might assume that the violent heat and pressure of a meteorite impact would incinerate any delicate organic compounds, effectively sterilizing the incoming material. However, research has shown that while the outer layer of a large asteroid or comet certainly vaporizes upon atmospheric entry, the interior can remain surprisingly cool. A significant fraction of the rock can be gently decelerated and deposited on the surface intact, its precious chemical cargo preserved within. Furthermore, we know that certain hardy microorganisms, like some species of bacteria, can enter a dormant, spore-like state that allows them to survive the extreme conditions of space, including intense radiation, vacuum, and freezing temperatures for astonishingly long periods. While the notion of fully fledged life surviving an interstellar journey is far more speculative, it is not entirely outside the realm of physical possibility, especially if that life were nestled deep within the protective bulk of a large rocky body. This theory elegantly reframes the question of life's origins from a local mystery to a galactic one. If panspermia is a viable process, then life may not need to invent itself independently on every single habitable world. Instead, it might only need to arise once in one favorable location somewhere in the galaxy. From that single genesis point, it could then spread, carried by the natural dynamics of planetary systems, seeding neighboring stars over billions of years. This idea of lithopanspermia, where life travels inside rocks, suggests our entire galactic neighborhood could be biologically connected. A large impact on Mars, for instance, could have ejected Martian rocks containing microbes into space, and some of those rocks could have eventually made their way to Earth. If we ever find life on Mars, a pivotal question will be whether it represents a separate genesis or a long-lost cousin, a branch on our own family tree that was transplanted by a cosmic event in the distant past. Now let's journey into the heart of a dark molecular cloud, a place so profoundly cold that the very rules of chemistry as we know them begin to shift. In these frigid nurseries of future stars, temperatures can plummet to just 10 degrees above absolute zero. At such extremes, the familiar dance of chemical reactions, driven by atoms and molecules colliding with enough energy to overcome their mutual repulsion, effectively grinds to a halt. Most particles simply don't move fast enough to react. They bounce off one another like lethargic billiard balls, unable to forge the new bonds needed to build complexity. For decades, this posed a monumental puzzle. If classical chemistry is too slow in these clouds, how do we explain the astonishing abundance of complex molecules that our telescopes clearly detect within them? The answer, it seems, lies in the bizarre and counterintuitive world of quantum mechanics and a phenomenon known as quantum tunneling. In our everyday classical world, think of trying to roll a ball over a steep hill. The ball needs a certain amount of kinetic energy to reach the top of the hill and roll down the other side. If it doesn't have that energy, it simply rolls back. This is analogous to the energy barrier that two atoms must overcome to get close enough for their electron clouds to interact and form a chemical bond. In the cold of a molecular cloud, most atoms lack the thermal energy to get over this hill. Quantum tunneling, however, offers a spectacular shortcut. It's as if the ball, instead of needing to go over the hill, had a small but real probability of simply appearing on the other side without ever climbing it. On the quantum scale, particles like atoms and electrons don't have definite positions. They are described by wave functions, which represent a cloud of probability. This wave function has a tiny, yet non-zero, chance of extending through an energy barrier that would be insurmountable in classical physics. When this happens, the particle hasn't jumped the barrier. It has, in a very real sense, tunneled directly through it. This quantum trick is not just a theoretical curiosity. It has a profound and practical impact on cosmic chemistry. The formation of molecular hydrogen, the most abundant molecule in the universe, provides the quintessential example. In the vast emptiness of space, the dominant form of hydrogen is the single atom. For two of these atoms to come together and form a stable H2 molecule, they must shed the considerable binding energy released during their union. If they can't release this energy efficiently, they will simply bounce apart. On the pristine surfaces of interstellar dust grains, this process finds its perfect stage. A single hydrogen atom drifting through the void can stick to an icy dust grain and begin a slow quantum mechanical crawl across its surface. When two of these adsorbed atoms tunnel toward each other, they can meet and combine. The dust grain itself acts as a crucial third body, absorbing the excess energy of the reaction and stabilizing the newly formed hydrogen molecule, which can then float away back into the gas. Without quantum tunneling facilitating this slow, cold migration and reaction on the grain surfaces, the universe would be starved of the very molecular hydrogen that fuels star formation and serves as the primary feedstock for all subsequent chemistry. But the influence of tunneling doesn't stop with hydrogen. It is likely the hidden catalyst behind the formation of far more complex molecules, including the water that fills our oceans. The prevailing theory for water's abundance suggests it forms in a series of steps on the icy mantles of these same dust grains. It begins with an oxygen atom bonding to a hydrogen atom to form a hydroxyl radical, or O. This OH radical is highly reactive, but in the deep cold, it should struggle to find and react with another hydrogen atom to form water, H2O. Classical mechanics would make this second step incredibly slow. Quantum tunneling, however, allows that second hydrogen atom to tunnel through the energy barrier to reach the waiting OH, enabling the completion of a water molecule even at temperatures where all motion seems frozen. This process, repeated countless times across millions of years within a single cloud, can build up thick layers of water ice, which later become incorporated into comets and planetesimals, ultimately delivering the water of life to young worlds like our own. This revelation fundamentally changes our understanding of the cosmic timeline for chemistry. If molecular clouds had to rely solely on rare, high-energy events or wait for pockets of warmer gas to drive classical reactions, the universe would be a much less chemically interesting place. Quantum tunneling provides a continuous, low-energy production line that operates relentlessly in the darkest and coldest regions of space. It means that complex molecular synthesis isn't just a feature of violent stellar deaths or the warm environments around young stars. It is a quiet, background process happening everywhere all the time, even in the most seemingly inert environments. The intricate organic molecules we've discovered, from sugars to PAHs, may owe their very existence to these subtle quantum effects that allow chemistry to proceed against all classical odds, proving that the universe has one more clever trick up its sleeve for building complexity from simplicity. As we move from the chaotic chemical soup of the early universe to the organized structures of life, we encounter one of the most elegant and puzzling mysteries in all of science, the phenomenon of homochirality. To understand this, you first need to grasp the concept of chirality itself. Picture your two hands. They are mirror images of each other, possessing the same components, 4 fingers and a thumb, yet you cannot superimpose one perfectly onto the other. No matter how you rotate them, your left glove will never fit your right hand. In the molecular world, the exact same principle applies. Many complex organic molecules, including the amino acids that build proteins, are chiral. They can exist in 2 distinct mirror image forms, often labeled as left-handed and right-handed. In a purely non-biological chemical reaction, these 2 forms are always produced in a perfect 50-50 ratio. They are chemically identical in almost every way, like a pair of identical twins who are perfect mirror images. Yet when we examine the chemistry of life on Earth, a stunning and absolute bias is revealed. Nearly every single amino acid found in every protein of every living organism is exclusively the left-handed version. Similarly, the sugars that form the backbone of our DNA and RNA are almost exclusively right-handed. This universal preference, this one-handedness of life, is what scientists call homochirality. It is a fundamental signature of biology, as consistent a law as gravity. But why would life, which seems to have arisen from a chaotic and random chemical beginnings, settle on such a specific and uniform handedness? This isn't a trivial detail. For life's most intricate machinery to function, for proteins to fold into their precise, functional shapes, and for DNA's double helix to form correctly, this homochirality is absolutely essential. A mix of both left and right-handed molecules would create a kind of molecular static, preventing the complex, tightly fitting structures of life from ever assembling. So the question becomes, what was the initial cosmic nudge that broke the symmetry and tipped the scales in favor of one hand over the other? One of the most dramatic theories points to events of almost unimaginable violence occurring light years away from our infant planet, the death throes of massive stars. When a giant star explodes as a supernova, or when the super-dense remnants of a dead star known as neutron stars collide, they do not just blast material into space. They also emit an intense and highly focused beam of radiation. This isn't ordinary light, it is circularly polarized light, a type of radiation that twists as it travels through space, corkscrewing either to the left or to the right. This unique property gives it a subtle but potentially decisive influence over chiral molecules. As this twisted light travels across the galaxy and passes through vast molecular clouds, it can interact differently with the left and right-handed versions of amino acids floating there. The radiation could preferentially destroy one chiral form over the other. Think of it as a cosmic filter. If a cloud were bathed in right-handed polarized light from a nearby stellar explosion, that light might more readily break apart the right-handed amino acids, leaving behind a slight but significant excess of the left-handed ones. This would imprint an asymmetry into the very raw materials of future solar systems before planets even began to form. This idea is bolstered by fascinating evidence from meteorites. Analyses of the famed Murchison meteorite, which we know was packed with amino acids, revealed something extraordinary. It wasn't a perfect 50-50 split. Researchers found a small but definite excess of left-handed amino acids in that ancient space rock. This tells us that a chiral bias was not something that originated on Earth. It was a condition delivered to Earth, a feature already present in the primordial inventory of our solar system. The most likely source of the polarized light needed to create this bias could be the frenetic environment of a neutron star, whose powerful magnetic fields can generate immense amounts of circularly polarized radiation. So, it's possible that the very handedness of every protein in your body was determined by the spin of a dying star that exploded billions of years ago, its final light etching a preference for left-handedness into the cosmic dust that would one day become us. However, the cosmos offers another, more grounded pathway for this selection, one that works not with cataclysmic light, but with the quiet, persistent chemistry of rock and ice. This theory centers on the surfaces of common minerals, which themselves can have a chiral geometry. Certain crystals, like quartz, can form in left-handed and right-handed varieties, their atoms arranged in mirror image spirals. On the early asteroids, where much of this probiotic chemistry was occurring, these chiral mineral surfaces could have acted as subtle molecular guides. As a random mixture of left and right-handed amino acids drifted through space and settled onto the surface of a left-handed quartz crystal, for instance, one form might fit more comfortably onto the atomic landscape than the other. This preferential adsorption could do two critical things. First, it would concentrate one chiral form, bringing those molecules closer together so they could more easily react and form chains. Second, and perhaps more importantly, the mineral surface could act as a template, actively promoting the formation of new amino acids in the favored handedness, effectively amplifying a tiny initial imbalance into a dominant majority. The journey from a slight excess to the absolute homochirality we see in life today might then have been completed by a process known as autocatalysis. Imagine a small, self-replicating chain of left-handed amino acids forms on one of these chiral mineral surfaces. This chain, by virtue of its own structure, might have the ability to act as a template or a catalyst that encourages the formation of more chains just like itself, using only left-handed building blocks. It's a kind of molecular chain reaction where the product of a reaction accelerates the production of more of itself. In an environment where left-handed molecules are even slightly more common, this autocatalytic process would quickly snowball, consuming the available feedstock and overwhelmingly producing left-handed polymers, while the orphaned right-handed molecules, lacking a template to guide them, remain as unused and disorganized scraps. This transition from a chemical preference to a self-replicating system marks the crucial leap from a simple mixture of molecules to the complex, functional, and organized chemistry that is the hallmark of all living things. So whether the initial nudge came from the twisted light of a stellar corpse or the gentle guidance of a crystalline surface, the universe appears to have had multiple ways of breaking its own symmetry, setting the stage for the one-handed life that would eventually evolve to ponder its own origins. While stellar explosions scatter the raw materials of life far and wide, another, more delicate structure was being woven in the final, gentle breaths of sun-like stars. In the beautiful and complex shells of gas known as planetary nebulae, astronomers have uncovered the existence of some of the most architecturally perfect molecules in the cosmos, fullerenes. Often called buckyballs after the visionary architect Buckminster Fuller and his geodesic domes, these molecules are hollow cages made entirely of carbon atoms. The most famous of these, C60, consists of 60 carbon atoms linked together in a pattern of alternating pentagons and hexagons, creating a structure that looks exactly like a microscopic soccer ball. Its larger cousin, C70, resembles a slightly elongated version of the same design. The discovery that these intricate carbon cages are not just laboratory curiosities, but are manufactured in abundance in the circumstellar envelopes of dying stars was a watershed moment in astrochemistry. The formation of these molecules is a testament to the precise conditions found in the stellar afterlife. When a star like our own Sun reaches the end of its life, it swells into a red giant, puffing off its outer layers in a series of gentle, slow-moving winds. This creates a dense, expanding shroud of gas rich in carbon, forged in the star's own core. As this shell expands and cools, the carbon atoms begin to link up. First, they form chains and rings, but in the right environment, one with just the right density and temperature, and shielded from the star's harsh ultraviolet radiation, they can self-assemble into these incredibly stable closed cages. The process is a kind of cosmic origami, where carbon atoms fold themselves into the most energetically favorable and resilient shape possible. The detection of their unique infrared fingerprints in the light from planetary nebulae provided incontrovertible proof that the universe is a master nano-engineer, capable of building symmetrical, complex molecules on a staggering scale. But the story doesn't end with the simple carbon cage. In the same nebulae, scientists have also found evidence for what are known as fullerenes. These are the hydrogenated versions of the buckyballs, where hydrogen atoms have attached themselves to the outside of the carbon cage, bonding to the carbon atoms. This might seem like a minor chemical detail, but it dramatically increases the molecule's potential as a cosmic asset. A pure C60 fullerene is already remarkably robust, capable of withstanding immense internal pressures and intense radiation. The addition of hydrogen atoms makes it even more stable and, crucially, more interactive with the surrounding interstellar environment. A fullerene is no longer just an inert carbon ball. It becomes a versatile organic platform, a kind of all-terrain molecular vehicle for traversing the harsh conditions of space. This unique stability unlocks one of the most compelling roles for these molecules, that of a protective shuttle for life's more fragile ingredients. Imagine the violent chaos surrounding a dying star. While the inner regions of a planetary nebula are relatively calm, the eventual exposure to interstellar space brings with it a barrage of ultraviolet radiation and cosmic rays that can easily shatter complex organic molecules. However, a fullerene or fullerene cage with its web of strong carbon bonds can act as an almost impenetrable safe. Laboratory studies have shown that these buckyballs can trap other atoms and even small molecules inside their hollow interiors. It is entirely plausible that within a planetary nebula, a C70 molecule could form around a simple amino acid like glycine, or even a molecule of water, sealing it away from the destructive forces outside. The molecule becomes a microscopic version of the pods used to transport seeds in the film Alien, a hardened capsule designed to protect its precious cargo through a period of extreme environmental stress. This concept of molecular protection extends the journey of probiotic materials across both space and time. After the planetary nebula disperses, these armored fullerenes are blown into the interstellar medium, where they can travel for millions of years. Their resilience allows them to survive the journey through regions of space that would be lethal to exposed, delicate compounds. When one of these molecular shuttles eventually becomes part of a new molecular cloud collapsing to form a new star and planets, it carries its protected payload right into the heart of a nascent planetary system. Upon entering the warmer, more chemically active environment of a protoplanetary disk, perhaps upon collision with another particle or when heated by the young star, the carbon cage could potentially crack open, releasing its preserved molecular passenger unharmed into the cosmic nursery. This mechanism provides an elegant solution to the problem of molecule survival, suggesting that the universe doesn't just manufacture the building blocks of life, it also fabricates sophisticated packaging to ensure their safe delivery to new worlds. While the frigid molecular clouds serve as vast chemical reservoirs and dying stars forge resilient carbon cages, the true construction site for new worlds offers its own dynamic stage for molecular innovation. This brings us to the bustling, spinning environments of protoplanetary disks, the magnificent pancake-like structures of gas and dust that swirl around infant stars, and the very cradles where planets themselves are assembled. Within these disks, the raw materials inherited from the interstellar medium are not merely passive passengers. They are subjected to a new and powerful source of energy that can reshape their chemistry: the intense ultraviolet radiation pouring from the tempestuous young star at the center. This is the realm of photochemistry, where light itself becomes the primary tool for building complexity, crafting molecules that will one day be woven into the very fabric of new planets. Imagine a disk that stretches for billions of miles, a chaotic maelstrom where microscopic dust grains are constantly colliding and sticking together, gradually building up from tiny specks into pebbles, then rocks, and eventually the seeds of planets. This entire structure is bathed in the harsh, energetic glow of its parent star, which in its youth is far more active and volatile than our middle-aged sun. This stellar ultraviolet light, or UV, carries much more energy than visible light. When a UV photon strikes a molecule, it doesn't just warm it up, it can deliver a sharp, precise kick enough to break chemical bonds apart. In the emptiness of space, this destructive force would simply shatter molecules into smaller fragments. But within the dense, crowded environment of a protoplanetary disk, and particularly on the surfaces of dust grains, this destruction becomes the catalyst for a new kind of creation. The process hinges on the dust grains themselves, which act as both a sanctuary and a workshop. As in the molecular clouds, these grains become coated in a frozen mantle of ices, water, carbon monoxide, methane, and ammonia. When a blast of UV radiation hits this icy mantle, it shatters the simple molecules trapped within, creating a chaotic soup of highly reactive fragments known as radicals. These radicals, desperate to form new bonds, are now held in close proximity on the grain's surface. They don't have to drift through space to find a partner, they are already neighbors frozen in place. This allows them to quickly and efficiently reassemble into new, more complex molecular structures that would be incredibly difficult to form through gas phase reactions alone. It's a bit like using a hammer to smash a collection of simple Lego bricks, only for them to spontaneously reassemble into a more sophisticated and intricate model right there on the workbench. This photochemical assembly line is remarkably productive. Astronomers observing protoplanetary disks with powerful telescopes like the Atacama Large Miller-Urey have detected the spectral signatures of a surprising variety of complex organic molecules. Among these are simple alcohols like methanol and a class of compounds known as ethers. These are not the exotic, fragile molecules of distant clouds. These are robust, stable compounds that serve as excellent stepping stones toward even greater complexity. Their formation through UV-driven chemistry on grain surfaces provides a continuous and efficient production mechanism right in the heart of the planet-forming region. This means that as the disk evolves, the very pebbles and planetesimals that are clumping together to form the cores of future worlds are already impregnated with these more advanced organic materials. They are not arriving later via comet impacts, they are being baked in from the very start, a fundamental ingredient in the planetary recipe. The location within the disk is crucial to this process. Too close to the young star, the intense heat would vaporize these ices entirely, leaving no frozen mantle for photochemistry to work upon. Too far out, the UV flux becomes too weak to drive the reactions effectively. The most active zone for this kind of chemistry is in the disk's warm midplane, a region often dubbed the soot line or beyond the ice line, where temperatures are just cold enough for volatiles to freeze but still receive a substantial amount of stellar radiation. This creates a sweet spot, a galactic Goldilocks zone for prebiotic chemistry, where conditions are just right for turning simple ices into a rich organic paste. The molecules forged here, sheltered within the growing planetesimals, are then in a perfect position to be delivered to the surfaces of rocky planets as they form, providing them with a rich, pre-processed chemical toolkit from day one. This theory beautifully connects the different chapters of our cosmic chemical story. It takes the simple molecules manufactured in cold molecular clouds and the hardy fullerenes forged in dying stars and subjects them to a final, local processing step within the planetary system itself. The protoplanetary disk acts as a final finishing school for prebiotic chemistry, using the abundant energy of its central star to upgrade its molecular inventory. The alcohols and ethers created in this way are far more than curiosities. They are versatile chemical agents. They can act as solvents, as building blocks for yet more complex structures, and as reservoirs of oxygen and carbon that can later participate in the aqueous chemistry on a young planet's surface. This suggests that the path to life is not reliant on a single miraculous event, but is instead a multi-stage industrial process spanning the galaxy and employing different tools, from quantum tunneling to photochemistry, at every step to ensure that when a new world is born, it arrives with a generous and diverse dowry of life's potential. Deep beneath the waves, far from the influence of sunlight or the chaos of asteroid impacts, the iron-sulfur world theory proposes that life's first metabolic processes were not born in the open ocean, but were literally forged in stone. This concept, pioneered by scientists like Gunther Wechtershauser, takes the hydrothermal vent hypothesis and gives it a powerful, specific chemical engine. It suggests that the very first steps toward a living system were not about building genetic molecules like RNA, but about establishing a continuous, self-sustaining cycle of chemical reactions that could harvest energy and build complexity, a primitive form of metabolism, all driven by the catalytic power of some of the most common minerals on the early Earth. At the heart of this theory are the unassuming, often brassy yellow crystals of iron sulfide and nickel sulfide, minerals like pyrite and maconite, which form in abundance at alkaline hydrothermal vents. These minerals are far from inert rocks. They possess a remarkable and almost magical catalytic ability. Pyrite, often called fool's gold, has a surface that can be both positively and negatively charged, creating an electrochemical landscape perfect for attracting and rearranging molecules. More importantly, the surfaces of these sulfide minerals are rich in dangling bonds and reactive sites that can act as a stand-in for the complex protein enzymes that drive metabolism in modern cells. In the porous, rocky matrix of a hydrothermal vent chimney, these minerals create a sprawling, three-dimensional catalytic network, a kind of inorganic scaffolding where the universe's first chemical innovations could take hold. The vent provides a constant, gentle flow of its key ingredients, hydrogen gas and hydrogen sulfide bubbling up from the geological underworld, and carbon dioxide dissolved in the surrounding ocean water. The iron and nickel sulfide catalysts provide the stage and the tools, and the natural proton gradient between the vent fluid and seawater provides the gentle, persistent push of energy to get everything started. The true elegance of this process lies in the chemical pathways it enables. Laboratory experiments simulating these vent conditions have demonstrated something astonishing. When hydrogen gas is passed over a catalyst of iron sulfide in the presence of carbon dioxide, under the moderate heat and pressure found at these vents, it readily produces simple organic molecules. The first and most foundational of these is acetic acid, the main component of vinegar. While it seems mundane to us, acetic acid is a 2-carbon molecule that sits at the very core of the metabolic cycle used by every single organism on Earth today. From this foundational piece, the chemistry can continue, with the help of other minerals like nickel sulfide, which is particularly good at handling reactions involving carbon monoxide. The process can build up to pyruvate. This is another pivotal metabolic molecule, a 3-carbon compound that is the universal entry point into the energy-producing cycle of all living cells. What we are seeing, in essence, is a non-biological geochemical mimicry of the most central metabolic pathways of life, running entirely on rocks and volcanic gases. This suggests a profound shift in how we imagine life's dawn. Instead of a genetics-first world where a self-replicating molecule like RNA was the initial breakthrough, the iron-sulfur world proposes a metabolism-first scenario. The very first system capable of evolution and growth may not have been a molecule enclosed in a membrane, but the mineral surface itself. Imagine a microscopic cavity within a vent chimney, its walls lined with catalytic iron sulfide. Here, a self-sustaining cycle of chemical reactions becomes established, consuming hydrogen and carbon dioxide and excreting acetic acid and other small organics. This cycle would be robust and self-perpetuating as long as the geological energy source lasted. Over immense spans of time, the organic products of this rocky metabolism would become more complex, eventually learning to coat the mineral surfaces and form their own organic barriers. The mineral scaffolding, in this view, acted as a kind of genetic template, not for storing information, but for directing a predictable and productive flow of energy and matter. A flow that would one day be inherited and refined by organic molecules into what we now recognize as life. But the universe's toolkit for building complexity isn't limited to the gentle warmth of hydrothermal vents or the specific frequencies of starlight. There exists another, far more powerful and ubiquitous source of energy, one that permeates every corner of the galaxy, silently and relentlessly. These are cosmic rays, not rays at all, but subatomic particles, primarily protons and atomic nuclei, accelerated to nearly the speed of light by the most violent events in the cosmos, such as supernova shockwaves and active galactic nuclei. They travel across immense intergalactic distances, and when one of these microscopic bullets slams into a molecule, it doesn't merely deliver a nudge, it delivers a sledgehammer blow, a catastrophic release of energy capable of completely rearranging matter. For a long time, this was seen as purely a destructive force, a source of radiation that would tear delicate organic molecules to shreds. Yet, a fascinating theory suggests that within this apparent chaos lies a creative potential, that cosmic rays could be the unexpected catalysts for one of the most critical steps in prebiotic chemistry, the act of polymerization, of linking small molecular units into the long, information-rich chains that are the hallmark of life. To understand this, we need to visualize what happens on a tiny, icy body in the outer solar system, like a comet or a Kuiper belt object. Its surface is a deep freeze, coated in a thick mantle of ice's water, ammonia, formaldehyde, and methanol. Embedded within this frozen matrix are the simple organic monomers we've discussed, like amino acids. In this frozen state, these molecules are largely inert. They lack the thermal energy to move around and link up. Now imagine a single cosmic ray proton traveling at a significant fraction of light speed, piercing through the void and slamming into this icy crust. The impact is not a gentle collision, it is a microscopic explosion. The particle tears through the ice, blasting apart water molecules and ripping electrons from their orbits, creating a localized, seething hot plume of ions and highly reactive radicals in its wake. This tiny, transient region, known as a thermal spike, can reach temperatures of thousands of degrees, but only for a vanishingly brief moment, a fraction of a microsecond, before the intense cold of the surrounding ice quenches it. It is within this fleeting, violent event that creation and destruction wrestle. While many molecules are undoubtedly shattered, the sudden, intense burst of energy and the dense soup of reactive fragments can also force connections that would otherwise be statistically impossible. The radical's molecular fragments with unsatisfied bonds created by the impact are thrown into extreme proximity. As the thermal spike cools almost instantly, these desperate fragments don't have time to drift apart. They are frozen in place, forced to bond with whatever is next to them. This can lead to the formation of new, more complex molecules. But more importantly, if the initial monomers are present, the energy can knock off a small molecule like water, allowing the carbon atoms of two amino acids to link directly together, forming a peptide bond. This is the fundamental reaction for building proteins, and a cosmic ray impact could, in effect, perform this chemistry by brute force, forging the first dimers, trimers, and perhaps even longer chains right there in the deep space ice. This process transforms every icy body in the solar system into a potential chemical factory. Unlike photochemistry, which only affects the very surface of an ice grain, cosmic rays are deeply penetrating. High-energy particles can travel meters deep into a comet's nucleus, driving this polymerization chemistry throughout its bulk. This means that the interior of a comet is not a pristine, frozen relic. It is a volume that has been continuously processed over billions of years by this relentless cosmic radiation. Every cubic inch contains the fossilized tracks of countless cosmic ray impacts, each one a tiny, failed or successful experiment in molecular chain building. The resulting material would not be a pure substance, but a complex, tarry mixture often referred to as an irradiation residue, containing everything from simple molecules to complex cross-linked polymers. When such a comet later enters the inner solar system and is warmed by the sun, these complex molecules, forged in cold and darkness by the most energetic particles in the galaxy, are released and could be delivered intact to a waiting planet like Earth. The evidence for this theory isn't just speculative. It comes from both laboratory experiments and space missions. Scientists have recreated these conditions by taking ices of simple molecules and bombarding them with proxies for cosmic rays, such as high-energy protons from particle accelerators. The results are unequivocal. These irradiated ices consistently produce a rich array of complex organics, including the building blocks of proteins and, crucially, the signature of peptide bonds themselves. Even more compellingly, the data returned from missions like the European Space Agency's Rosetta probe, which studied comet 67P/Churyumov-Gerasimenko, revealed that the comet's surface was much harder and more complex than expected, with a crust that appeared to be a polymerized organic layer, consistent with the kind of material produced by long-term cosmic ray processing. This suggests we are not just theorizing about a possible process. We are observing its real-world product sailing through our solar system today. What makes cosmic ray-induced polymerization so compelling is its sheer universality and inevitability. While other energy sources might be localized, a hydrothermal vent here, a sun-warmed pond there, cosmic rays are everywhere. They bathe the entire galaxy, ensuring that no icy body, from a comet in our own Oort cloud to a moon orbiting a planet in a distant star system, is exempt from this continuous processing. This theory implies that the first steps toward biological polymers, the chaining together of monomers, may not be a rare or special event. It could be a standard, ongoing geological process on countless frozen worlds across the Milky Way. The universe, it seems, employs every tool at its disposal, from the subtle quantum trickery of tunneling to the overwhelming force of relativistic particles, to ensure that the path from simplicity to complexity is not just a possibility, but a pervasive and actively driven phenomenon throughout the cosmos. Yet, for all the focus on the intricate chemistry of replication and metabolism, a fundamentally different school of thought asks a simpler, more architectural question. What if the very first spark of life wasn't about information at all, but about creating a boundary, a protected, private space where chemistry could become truly personal? This is the core of the lipid world hypothesis, a perspective that shifts the spotlight away from the familiar stars of the origin of life story, RNA and proteins, and onto a cast of molecules often relegated to a supporting role, lipids. These are the fatty, water-insoluble molecules that form the foundation of every cell membrane in your body today. The radical proposal here is that long before the first gene was replicated or the first metabolic cycle spun, the universe's first act of true biological organization was the spontaneous formation of a tiny, self-contained bubble, a protocell. The magic of lipids lies in their inherent duality, a molecular personality that is perfectly suited for creating order from chaos. A typical lipid molecule has a head that is attracted to water and a tail that repels it. When a large number of these molecules are floating freely in an aqueous environment, like the early Earth's oceans or even a small pond on an asteroid, they don't remain scattered for long. Driven by the simple physical need to hide their water-fearing tails and expose their water-loving heads, they self-assemble. They spontaneously organize into incredibly stable, sheet-like structures called bilayers, 2 molecules thick, with all the tails pointing inward, shielded from the water, and all the heads facing outward, bathing in it. And when these sheets are disturbed or simply form in a turbulent environment, they naturally curl in on themselves and seal their edges, forming perfectly closed spherical compartments known as vesicles. These are, in essence, the universe's first protocells, and their formation requires no enzymes, no genetic instructions, and no external energy source. It is a built-in physical inevitability given the right ingredients. This act of compartmentalization is far more profound than just creating a simple container. It represents the birth of individuality and the very concept of an inside versus an outside. Within the confines of a lipid vesicle, the chemical environment is suddenly and dramatically different from the vast, dilute ocean beyond its wall. Molecules trapped inside are concentrated, dramatically increasing the odds that they will bump into each other and react. A reaction that would be statistically negligible in the open water can become frequent and robust within the tiny volume of a vesicle. Furthermore, the vesicle's membrane acts as a selective barrier. It can allow small molecules like water or simple nutrients to passively diffuse in while keeping larger, more complex products safely trapped inside, preventing them from simply drifting away and being lost. This creates a positive feedback loop. Successful reactions inside the vesicle lead to a buildup of complex products, which in turn makes the vesicle a more potent chemical factory compared to its surroundings. It's the origin of competition, where the most successful chemical systems are the ones that get to persist and grow. But the role of lipids in this early world may have extended far beyond just being passive walls. Certain types of lipids are not just structural, they are chemically active. Some can act as primitive catalysts themselves, their surfaces providing a unique environment that can speed up specific chemical reactions, much like the mineral surfaces at hydrothermal vents. Imagine a lipid vesicle whose membrane is composed of a mixture of different fatty molecules. One particular lipid might have a head group that attracts and holds 2 other small molecules in just the right orientation, encouraging them to link together. This means the vesicle isn't just a container for chemistry. Its very walls are participating in the chemistry, creating a tightly integrated system where structure and function are one and the same. This synergy between compartmentalization and catalysis presents a powerful alternative to the genetics first or metabolism first scenarios. It suggests that the first evolving systems could have been these simple, self-reproducing lipid vesicles, competing with one another based on the stability of their membranes and the efficiency of the reactions they could catalyze. The evidence for this hypothesis is not just confined to computer models. It can be recreated in any modern laboratory. When researchers take simple fatty acids, which would have been plentiful on the early Earth, and mix them with water, they can watch under a microscope as countless vesicles form and bud and divide, behaving in an eerily lifelike manner. Even more strikingly, if you provide these vesicles with fresh lipid building blocks, they can grow. And as they grow, they become unstable, eventually pinching in the middle to split into 2 daughter vesicles, a primitive form of self-reproduction. Some of these daughter vesicles can even inherit the chemical character of their parent, maintaining a kind of compositional inheritance without a single strand of RNA in sight. This shows that properties we associate with life growth, division, and a form of inheritance can emerge from the simple physics of lipids alone. The lipid world hypothesis doesn't necessarily dismiss the importance of RNA or proteins. Instead, it provides a plausible home for them. A lipid vesicle offers the perfect sheltered environment for a fragile, early RNA molecule to experiment with self-replication without being diluted or destroyed. It creates a protected stage where the slow, patient chemistry of the iron-sulfur world could become concentrated and refined. In this view, lipids provided the essential architectural breakthrough, the invention of the private property that allowed for the accumulation of wealth, in this case, chemical wealth. They created the first autonomous individuals, setting the stage for a new kind of evolution, one where these simple bubbles could begin to compete, and the most successful chemical partnerships held within them would be the ones passed on to fuel the next, more complex chapter in the great story of life. But to truly grasp the scale of this cosmic chemistry, we must zoom out from individual dust grains and comets to behold the grandest laboratories of all, the giant molecular clouds themselves. These colossal structures, sprawling across hundreds of light years and containing the mass of millions of suns, are not just passive storage lockers for pre-made molecules. They are dynamic, bustling chemical metropolises, vast three-dimensional reactors where the future molecular diversity of entire star systems is being actively manufactured. Imagine a city with distinct industrial districts, each with its own specialized conditions and output. A giant molecular cloud operates on a similar principle, with a complex internal architecture of varying density, temperature, and radiation exposure that creates a stunning array of chemical environments all under one cosmic roof. At the diffuse, turbulent outer edges of the cloud, where the harsh ultraviolet light from nearby young, massive stars can still penetrate, a very specific kind of chemistry dominates. Here, UV photons are powerful enough to tear molecules apart, but this destruction also creates a frontier of intense activity. This region is known as a photodissociation region, and it's where we find some of the most complex carbon-based molecules, including the polycyclic aromatic hydrocarbons. The relentless radiation breaks down larger carbon chains and structures, but in the process, it provides the energy and the reactive fragments that can quickly reassemble into these sturdy, ringed molecules on the surfaces of dust grains. It's a bit like a high-energy recycling plant, where old molecular structures are broken down and their components are used to forge new, more resilient materials designed to withstand the very radiation that created them. Further inside, as the cloud grows denser and starts to block out the most damaging stellar radiation, the chemistry shifts. The environment becomes cooler and more shielded, allowing the delicate sugars and precursor molecules like formaldehyde to accumulate on the icy mantles of dust grains through the slow, patient processes of cold surface chemistry and quantum tunneling. This layered structure means that a single giant molecular cloud is not producing a uniform chemical soup. It generates a rich, spatially organized gradient of molecular complexity. In the cold, dark, and incredibly dense cores at the very heart of the cloud, the same cores that are on the verge of collapsing to form new stars, the chemistry enters its most protected phase. Here, shielded from virtually all external radiation, the icy dust grains become thick with frozen volatiles. In these deep freeze conditions, even the simplest molecules can slowly, over millions of years, link up into more complex structures. It is in these frigid nurseries that astronomers believe some of the most delicate probiotic molecules, like the amino acid glycine, are finally assembled in peace, sheltered from the chaotic energy of the wider galaxy. The cloud, therefore, acts as a complete industrial pipeline, taking raw atomic ingredients at its outskirts and processing them through successive stages of refinement until, in its deepest sanctums, it outputs the most sophisticated chemical products in its inventory. This organized chemical production has a direct and profound consequence for the planetary systems that will eventually form. When a dense core within the cloud finally collapses under its own gravity to birth a new star, it does not do so with a homogeneous mix of gas and dust. Instead, the entire protoplanetary disk that swirls into existence around the infant star inherits this pre-processed chemical gradient. The material in the outer disk, which originated from the cloud's cold, dense interior, will be incredibly rich in water, ice, and complex organics. Meanwhile, material from the cloud's warmer, more irradiated outer layers, now located in the inner disk, will carry a different chemical signature, perhaps richer in resilient molecules like PAHs. This means that from their very inception, different planets forming at different distances from the star start with fundamentally different chemical toolkits. An icy body forming in the outer system will be endowed with a treasure trove of prebiotic molecules forged in the cloud's deepest freeze, while a rocky world in the inner system might receive a greater abundance of carbon-based building blocks that survived the hotter, more energetic conditions. The sheer longevity of these clouds is what makes their chemical output so significant. A giant molecular cloud can exist for tens of millions of years, an almost unimaginably long time for chemical reactions to proceed. While individual reactions on a dust grain might be slow, the collective action of trillions upon trillions of grains, each acting as a microscopic laboratory, operating in parallel for millions of years, can produce staggering quantities of complex material. Every single one of the countless chemical pathways we've explored, from the formation of molecular hydrogen via quantum tunneling to the ultraviolet-driven synthesis of sugars, is operating simultaneously and continuously throughout the vast volume of the cloud. This isn't a sporadic or rare event. It is a constant background hum of molecular creation, a foundational process of the galaxy. The cloud is not merely a birthplace for stars. It is a prolific factory that ensures every new generation of stars and planets begins its life with a rich, diverse, and preceded inventory of the very molecules that can kickstart the journey toward life, making these dark, swirling nebulae the ultimate cosmic cradles for biological potential. Now let's shift our focus from the deep oceans and the frigid void of space to the seemingly mundane substance beneath our feet, clay. It is almost paradoxical to imagine that the soft, pliable mud we associate with pottery and riverbanks could have played a starring role in the origin of life. Yet one of the most fascinating theories suggests that the intricate crystalline surfaces of certain minerals provided the universe with its first scaffolds and assembly lines for complex molecules. This idea, most famously championed by the chemist Alexander Graham Cairns-Smith, proposes that long before RNA or proteins took over, lifeless, inorganic crystals were the pioneers of information storage and replication, acting as a kind of genetic material for a primitive, mineral-based form of evolution. Cairns-Smith's radical hypothesis, often called the clay world theory, begins with a simple but profound observation. The most fundamental property of life is its ability to store and transmit information, a role performed in all modern organisms by the long, complex chains of DNA and RNA. But how could such sophisticated polymers have arisen from a random chemical soup? Cairns-Smith argued that they probably didn't, at least not directly. Instead, he proposed an intermediary step, a simpler, cruder form of information storage that nature had already perfected: the crystal structure of certain clay minerals. Imagine a crystal of a common clay like kaolinite growing slowly in a puddle on the early Earth. Its surface is not a random jumble of atoms. It is a perfectly ordered, repeating lattice, a two-dimensional landscape of hills and valleys with a specific, predictable pattern. If a flaw occurs during its growth, a misplacement of an atom, or the incorporation of an impurity like nickel instead of magnesium, that flaw can be replicated as the crystal continues to grow, propagating the mistake in new layers. In this sense, the crystal is storing a form of information in its atomic arrangement, and it is passing that information on as it expands, a primitive, inorganic form of inheritance. This crystalline genetics sets the stage for a rudimentary kind of evolution. In a pool rich with different dissolved minerals, various types of clay crystals would form and grow, each with its own distinct surface pattern. Some crystal structures, by sheer chance, might have properties that give them a competitive edge. One type of clay might grow faster in the local conditions, outcompeting its neighbors for raw materials. Another might be more stable, resisting dissolution when the pond's chemistry changed. A third, and this is the crucial leap, might have a surface that incidentally catalyzed the formation of organic molecules. The crystals that were best at surviving and replicating their structure would become the dominant forms in their environment. Over immense spans of time, this process of selection would refine these mineral genes, favoring the crystals that were not only robust but also chemically productive, effectively breeding a generation of minerals that were pre-adapted to assist in the emergence of organic life. The true power of these selected clays lies in their dual role as both a catalyst and a template. The surfaces of many clay minerals are not smooth and inert, they are bustling with chemical activity. They carry localized electrical charges that can attract and hold simple organic molecules like nucleotides or amino acids, concentrating them from the dilute primordial soup and bringing them into close proximity. This dramatically increases the likelihood that these molecules will react with each other. But clays do more than just gather ingredients, they also act as matchmakers. Their crystalline lattices have specific spacings between their atoms that can hold the building blocks of RNA in just the right orientation, encouraging them to link together into a chain. It's like a molecular assembly jig in a factory, holding pieces in the perfect position so they can be snapped together efficiently. Laboratory experiments have repeatedly confirmed this, showing that when simple nucleotides are washed over certain types of clay, they can spontaneously form short chains of RNA, a reaction that is incredibly slow and inefficient in water alone. The clay isn't just speeding up the process, it is providing the essential organizational framework, the blueprint for the polymer's structure. This theory provides an elegant solution to one of the most vexing problems in the RNA world hypothesis. How could the first long, functional RNA molecules have assembled without the help of modern protein enzymes? The answer may be that they had mineral helpers. The clay surface acts as a non-biological enzyme, a ribozyme before ribozymes existed. Furthermore, the specific pattern of charges on the clay's surface could have acted as a selection pressure, favoring the formation of certain sequences of nucleotides over others. A crystal lattice with a particular spacing might preferentially assemble nucleotides that fit that pattern, effectively coding for a specific, simple RNA sequence. Over time, as these organic molecules became more complex and began to take on the functions of catalysis and self-replication, they would have eventually outcompeted their mineral mentors. The organic world, in Cairns Smith's poetic phrasing, performed a genetic takeover, hijacking the informational and catalytic principles first invented by the crystalline world and translating them into the far more versatile and powerful language of carbon-based chemistry. So, the next time you see a patch of wet clay, consider the possibility that you're looking at the faded, mineral fossil of life's first and most humble ancestor. While our gaze has been fixed on Earth's oceans and the deep void between stars, one of the most vivid demonstrations of the universe's chemical creativity is happening right now in our own solar system, on a world that looks nothing like our own. High above the hazy orange atmosphere of Saturn's largest moon, Titan, the Cassini spacecraft's instruments detected a profound mystery. The surface was hidden beneath a thick photochemical smog, but radar and infrared data revealed a landscape of dark, dune-filled deserts and lighter, elevated terrain, all stained with a strange, reddish-brown organic material. This substance isn't a simple molecule. It is a class of complex chemical compounds known as tholins, and their existence on Titan provides a stunning new window into how the universe can manufacture the building blocks of life under conditions we once thought were utterly hostile to such complexity. The story of tholins begins not on a moon but in a laboratory. In the 1970s, the astronomers Carl Sagan and Bishon Carr were attempting to simulate the atmosphere of Titan, which we knew was primarily nitrogen with a small percentage of methane. In their experiments, they mixed these simple, boring gases in a chamber and then subjected them to a source of energy meant to mimic the sunlight that bathes Titan, in this case an electrical discharge. What they witnessed was astonishing. The clear, colorless gases slowly transformed, producing a sticky, reddish-brown resin that coated the inside of their apparatus. This gunk wasn't a single, well-defined molecule. It was a complex tar-like polymer, a chaotic tangle of carbon, hydrogen, and nitrogen atoms linked together in a myriad of unpredictable ways. Sagan and Carr named this class of substances tholins, from the Greek word for muddy, and they realized they had discovered a powerful and universal chemical pathway. Whenever simple carbon-bearing gases like methane are exposed to energy in a non-oxidizing atmosphere, the universe seems predisposed to cook up this complex organic goo. Titan itself is the perfect natural laboratory for this process. Its cold, dense atmosphere is a chemical factory running continuously on a global scale. High in its stratosphere, ultraviolet light from the distant sun and impacts from Saturn's powerful magnetosphere provide a constant stream of energy. This energy shatters the stable molecules of nitrogen and methane, creating a zoo of highly reactive fragments and radicals compounds like ethylene, hydrogen cyanide, and cyanocetylene. These fragments are the building blocks for the tholins. They quickly begin to link together, forming larger and more complex molecules in the upper haze layers. These particles slowly drift down through the atmosphere, growing as they fall, eventually settling on the moon's surface like a slow, persistent drizzle of organic snow that has been accumulating for possibly billions of years. This is why Titan's surface is coated in these materials. The entire moon is being showered in the products of its own atmospheric chemistry. The implications of this go far beyond a single moon. Titan presents us with a fundamentally different model for prebiotic chemistry than Earth. On our planet, liquid water is the essential solvent, the medium in which life's molecules dance and interact. On Titan, with surface temperatures of -180 degrees Celsius, water is frozen solid, harder than granite. Instead, the role of liquid solvent is played by methane and ethane, which exist in a liquid state, forming rivers, lakes, and even great seas. This means that the tholins raining down from the sky aren't just landing on a barren, frozen wasteland. They are washing up on hydrocarbon shores, dissolving in methane lakes, and being concentrated by evaporation and rainfall in a hydrological cycle eerily similar to Earth's, but with completely different chemistry. We don't yet know what happens when these complex tholins are given geologic time to stew and interact in these liquid hydrocarbon pools. Could they fold into more structured forms? Could they engage in a kind of chemistry that leads to even greater complexity, perhaps even a system we would recognize as life, but based on a completely different biochemistry? The possibility is both thrilling and humbling. This process is almost certainly not unique to Titan. Any cold body in the outer solar system with a source of methane and a tenuous atmosphere could be undergoing a similar transformation. Pluto, for instance, with its stunningly complex landscape and reddish-brown patches of terrain, is almost certainly coated in its own variety of tholins, created as the weak sunlight on its methane and nitrogen ices drives the same kind of chemistry. The countless Kuiper belt objects and cometary nuclei that dwell in the frigid outer darkness are also likely repositories for these substances. They represent a vast, frozen reservoir of pre-processed organic material, a cosmic stockpile of life's potential building blocks that has been manufactured and stored in deep freeze since the solar system's birth. When a comet from this reservoir plunges into the inner solar system, the heat from the sun warms its surface, releasing not just water vapor and dust, but also this complex organic tar, delivering it to planets like the early Earth. The significance of tholins lies in their role as a universal intermediary. They are the messy, chaotic, but incredibly productive middle step between the utter simplicity of gases like methane and the elegant, specific structures of biological molecules. In laboratory experiments, when scientists take tholins synthesized to mimic Titan's conditions and place them in contact with liquid water, simulating what might happen if a tholin-rich comet struck the early Earth, something remarkable occurs. The complex polymers begin to break down, releasing a wide array of recognizable biological building blocks. They produce all 20 of the amino acids used by life on Earth, as well as the nucleobases that form the letters of the genetic code. This means that tholins are not a dead end. They are a rich prebiotic concentrate, a kind of all-in-one starter kit for organic chemistry. A single delivery of this material to a young, water-rich world could provide a massive and diverse infusion of the very compounds needed to jump-start the journey toward life. This transforms our view of the cosmos's chemical potential. We no longer need to imagine that every habitable world must independently invent all of its complex chemistry from scratch. Instead, the universe appears to have a default setting, a tendency to take the simplest and most common carbon-containing molecules, and whenever energy is available, process them into these complex organic tars. This tholin pathway operates efficiently in the cold, without liquid water, and in atmospheres very different from our own. It suggests that the initial steps toward life's chemistry are not rare or special, but are a standard, almost inevitable geological process on a vast array of icy worlds. The reddish stain we see on Titan and Pluto is not just a curious coloration. It is the signature of a fundamental cosmic process, a testament to the universe's relentless, persistent drive to build complexity from simplicity, using every tool and every environment at its disposal. Yet for all the elegant scaffolding provided by minerals and the protected environments of vents and vesicles, a critical question remains. How did the universe make the leap from chemistry that merely persists to a system that can evolve? How could a collection of molecules begin not just to exist but to innovate, to adapt, and to grow in complexity over time? The answer to this profound transition may lie with a single, multifaceted molecule and the theory that places it at the very center of life's dawn, the RNA world hypothesis. This idea proposes that before the intricate partnership of DNA and proteins ever existed, a simpler, more versatile molecule ruled the primordial world. Ribonucleic acid, or RNA, is imagined not as a mere messenger but as the original pioneer, a jack of all trades that could both hold genetic blueprints and actively construct things with its own hands. To understand why RNA is such a compelling candidate for the first self-replicator, you have to appreciate its unique dual nature. In all modern life, there is a clear division of labor. DNA is the magnificent, stable library, a master archive that stores the long-term genetic information for building an organism. Proteins are the workforce, the countless workers and machines that carry out nearly every function in the cell, from speeding up chemical reactions to providing structural support. But this elegant system presents a classic chicken and egg paradox. DNA requires specific proteins to unwind, copy, and read its information, yet the instructions for building those very proteins are encoded within the DNA itself. So which came first? The RNA world elegantly sidesteps this paradox by suggesting that, in the beginning, one molecule did both jobs. RNA, like DNA, is a chain made of nucleotides, and the specific sequence of those nucleotides can store information, acting as a primitive gene. But unlike the relatively inert DNA double helix, RNA molecules can fold into intricate three-dimensional shapes, and some of those shapes can act as catalysts, speeding up chemical reactions. These catalytic RNA molecules are called ribozymes, and their discovery in the 1980s was the thunderclap that made the RNA world hypothesis a central pillar of Origins research. Imagine a shallow pool on the early Earth, rich with the nucleotide building blocks of RNA, perhaps formed on clay surfaces or delivered by meteorites. Through random chemical processes, some of these nucleotides link up into short, single-stranded RNA chains. Most of these random chains are useless, but by sheer chance, one folds into a shape that gives it a slight advantage. Perhaps one ribozyme has a pocket that helps it grab free nucleotides and line them up. It might then act as a template, encouraging a complementary strand to form alongside it. This copying process would be clumsy and full of errors at first, but it would represent something the universe had never seen before, a molecule that could make copies of itself. This is the moment of genesis, the pivotal transition where a chemical system becomes subject to the laws of evolution. Once self-replication emerges, however imperfectly, variation and selection can begin. A random change in the sequence. A mutation might create a new ribozyme that copies itself faster, or one that is more stable in its environment. These more efficient replicators would outcompete their neighbors, consuming the available building blocks to become the dominant form. This is no longer just chemistry. This is the dawn of natural selection acting on molecules. The power of this molecular evolution is not just theoretical. Scientists have conducted breathtaking experiments in the lab, creating what is known as test tube evolution. They start with a vast soup of trillions of random RNA sequences and introduce a selective pressure. For instance, they might want an RNA molecule that can cut itself or ligate two pieces together. They then isolate the few molecules that show any hint of the desired activity, use enzymes to amplify their numbers, and repeat the process over many generations. Astonishingly, within just a few dozen cycles, the population of RNA molecules evolves, honing in on sequences that are highly efficient at the selected task. Researchers have evolved ribozymes that can perform a surprising range of functions that would have been critical in an RNA world, including synthesizing short RNA strands and even forming simple peptide bonds, the links that hold proteins together. This demonstrates that RNA is not just capable of storing information. It possesses a latent chemical potential that, when guided by selection, can blossom into a stunning array of functional complexity, all without the need for a single protein enzyme. Of course, the classic weakness of the RNA world has always been the inherent fragility of the RNA molecule itself, especially its sugar-phosphate backbone, which is more prone to breaking down than the backbone of DNA. And the spontaneous, prebiotic synthesis of its components, particularly the sugar ribose, has been a long-standing challenge, as we saw with the messy Formose reaction. However, recent research has uncovered fascinating pathways that suggest RNA might not have emerged fully formed. Instead, it could have been preceded by even simpler, more robust molecular cousins, often called pre-RNA worlds. Some scientists propose that the first genetic system might have used a different sugar in its backbone, like threose, which is simpler and more stable than ribose. Others suggest that the earliest replicators might have been peptide nucleic acids, or PNA, which use peptide bonds, the same bonds found in proteins, to hold their nucleotide bases together, creating a sturdy, hybrid molecule that could have acted as a transitional genetic system. Over time, through chemical evolution, this primitive system could have gradually refined itself, eventually standardizing on the RNA we know today as the most efficient compromise between stability, replaceability, and catalytic potential. The RNA world hypothesis provides the most coherent bridge we have from the chaotic chemistry of the early universe to the structured, information-driven biology that followed. It paints a picture of a planet where the first organisms were not cells, but naked, self-replicating RNA molecules evolving in a molecular Darwinian struggle. These primordial genes would have competed for space and resources, innovating new chemical tricks to survive. Some might have evolved to surround themselves with simple lipid membranes, becoming the first protocells and gaining a huge survival advantage. Others might have begun to synthesize short protein-like chains, eventually discovering that these proteins could perform certain tasks like metabolism far more efficiently than the ribozymes themselves. This would have set the stage for the great genetic takeover, where the more stable DNA eventually shouldered the responsibility of long-term information storage, and proteins took over the vast majority of catalytic work, leaving RNA in its modern, essential but more specialized roles. In this view, the RNA world was not the end point, but the revolutionary catalyst, the pivotal era where the universe learned how to learn, setting in motion the evolutionary journey that would eventually lead to the breathtaking diversity of life we see today. As we consider the bustling chemical factories of molecular clouds and protoplanetary disks, we encounter a remarkable cosmic preservation system, one that locks away the raw ingredients of life in a deep freeze vault for billions of years. This theory centers on comets, those ancient, icy wanderers from the outer solar system, which act as pristine time capsules, capturing a frozen record of our solar system's earliest chemistry. Far from being simple balls of dirty ice, comets are now understood as intricate chemical reservoirs, and their journey from the frigid outskirts of the planetary disk into the warmer inner solar system may have been the final, crucial step in activating the prebiotic potential stored within them for eons. The process begins in the cold, dark reaches of the young solar system, far beyond the orbit of the infant Jupiter, in a region where temperatures are so low that even gases like carbon monoxide, methane, and ammonia freeze solid onto any available surface. Here, in the protoplanetary disk's outer fringe, microscopic dust grains, the same ones that were processed in the molecular cloud, drift through this icy mist. As they do, they act like sticky snowballs, accumulating thick, layered mantles of frozen volatiles. Crucially, mixed in with these ices are the simple organic molecules manufactured earlier in the cloud's history or formed locally through photochemistry: formaldehyde, hydrogen cyanide, methanol, and perhaps even simple amino acids. In the profound cold of this outer disk, approaching just a few tens of degrees above absolute zero, all molecular motion grinds nearly to a halt. Any chemical reaction that requires significant energy becomes impossibly slow. This isn't a place for building complexity, it is a place for perfect preservation. The molecules become trapped, frozen in place within the crystalline matrix of water ice, like insects suspended in amber. They are effectively put into a state of suspended animation, shielded from radiation and protected from the warmer, more reactive environments closer to the sun. This act of deep freeze trapping is what gives comets their incredible value as cosmic archives. When these icy dust grains slowly accrete through gentle collisions, building up over millions of years to form the nuclei of comets, they are not homogenizing their content. Instead, they are creating a layered, sedimentary record, a kind of frozen stratigraphy that preserves a snapshot of the chemical conditions at the time and place of their formation. A comet born in the Kuiper belt beyond Neptune would have a different chemical signature than one from the more distant Oort cloud, each one a unique time capsule from a specific neighborhood in the early solar system's construction zone. The key is that this material has remained largely unchanged for 4.5 billion years, offering us a direct sample of the primordial ingredients that were available before the planets finished forming. The preservation, however, is only half the story. The true magic of this cold trap theory unfolds when these frozen time capsules are nudged from their stable orbits and begin their long fall toward the inner solar system. As a comet approaches the sun, the increasing solar radiation begins to warm its surface, triggering a dramatic transformation. The ices on the surface don't just melt, they sublimate, turning directly from solid ice into gas, which erupts outward to form the comet's magnificent glowing coma and tail. But this warming does not happen uniformly or instantly throughout the comet's nucleus. The heat from the sun penetrates only a short distance, creating a thermal gradient from the hot surface to the still frozen interior. It is within this dynamic boundary layer, where temperatures are rising but have not yet vaporized everything, that a brief and fertile window for new chemistry opens. Imagine the scene inside the warmed crust of a comet. For the first time in billions of years, the trapped molecules are thawing and gaining mobility. Water ice becomes a temporary liquid in microscopic pockets, a fleeting solvent that allows previously isolated molecules to mix and interact. Formaldehyde, trapped for eons next to hydrogen cyanide, can now react. The energy from the sunlight itself can provide the activation energy needed to drive these reactions forward. This is where the simple precursors, preserved in their pristine state, can be upgraded into more complex structures. The same formose reaction that can create sugars from formaldehyde could be initiated in these warm cometary ices. The reactive fragments created by cosmic ray damage over billions of years could now find partners and combine. This means the comet is not just a passive delivery vehicle, it is an active, mobile chemical reactor. As it journeys sunward, it is literally cooking its own ingredients, transforming a preserved mixture of simple organics into a richer, more complex broth of prebiotic compounds. This process of cometary activation is dramatically amplified by shock events. The early solar system was a violent shooting gallery, and comets were frequent targets. A collision between two comets, or even a close gravitational encounter with a planet, would generate immense shock waves that travel through the icy material. A shock wave compresses and heats material almost instantaneously, creating localized pockets of extreme pressure and temperature that can last just milliseconds. But that is more than enough time to drive chemistry at an explosive rate. Laboratory experiments that simulate these shock conditions by firing projectiles into ice mixtures have shown spectacular results. A frozen blend of simple, common cometary ices like water, methanol, and ammonia, when subjected to a sudden shock, can produce a wide array of complex amino acids. The violent energy of the impact provides the forceful nudge needed to snap molecules together in ways that gentle warming alone cannot achieve. The culmination of this entire sequence, preservation, warming, and shock activation, is the delivery of this upgraded material to terrestrial planets. When a comet, now enriched with a more complex set of organic molecules, eventually collides with a young world like Earth, it does more than just cause a catastrophic explosion. It performs a grand act of inoculation. The heat of atmospheric entry and impact would certainly destroy a significant portion of the comet's volatile material, but studies suggest that a substantial fraction of the comet's interior can remain relatively cool. Complex organic molecules embedded deep within the comet's nucleus can survive the journey and be deposited on the planet's surface intact. Furthermore, the immense plume of material ejected from the impact site could itself act as a chemical reactor, with the shock of the impact generating yet another round of synthetic chemistry in the expanding vapor cloud, creating entirely new compounds that then rain down across the globe. This theory elegantly links the cold, patient chemistry of the interstellar medium with the warm, dynamic environment of a young planet. Comets are the indispensable couriers in this story, providing both the raw materials and the final processing step. They gather the simple building blocks from the coldest corners of the planetary system, preserve them in a state of suspended animation for billions of years, and then, upon command from a gravitational nudge, transport them inward, using the energy of the sun and the violence of collisions to perform the last crucial upgrades to their molecular payload. This suggests that the emergence of life on Earth was not reliant on a single, fragile chain of chemical events happening in one location, but was instead bolstered by a continuous, system-wide infusion of pre-processed organic wealth, delivered by these icy messengers from the distant past, ensuring that our planet's primordial soup was both rich and diverse from the very beginning. But as we've seen, the universe rarely relies on a single method when multiple pathways are available. While cosmic rays work their silent, penetrating magic and the gentle warmth of hydrothermal vents fosters gradual chemistry, the birth of a star itself presents a stage for a far more dramatic and explosive form of synthesis. Picture the scene not on a planet, but in the swirling, chaotic envelope of gas and dust collapsing to form a new sun. This is a region of unbelievable turbulence, where immense gravitational forces are pulling matter inward at terrifying speeds, creating friction, shockwaves, and colossal electrical imbalances. Within this churning maelstrom, the theory of electric discharges in protostellar envelopes suggests that nature harnesses the raw power of lightning on a truly cosmic scale, not just as a rare spectacle, but as a fundamental and widespread engine for molecular creation. The scale of these discharges is almost beyond human comprehension. We are not talking about the lightning that crackles within a thundercloud on Earth, impressive as that is. In the vast, dusty shroud surrounding a protostar, the potential difference, the electrical voltage, can build to levels millions of times greater than anything our planet experiences. The particles of dust and ice, colliding violently as they spiral inward, can strip electrons from atoms, creating a massive charge separation. When this built-up energy finally discharges, it does so not in a single, forked bolt, but in colossal, continent-sized arcs that flash through the protoplanetary material. These are not brief flickers either. In the dense, extended environment of the envelope, such a discharge could be sustained, creating a temporary, searing hot plasma channel with temperatures soaring to tens of thousands of degrees. Within this fleeting stellar-scale furnace, the simple, robust molecules inherited from the molecular cloud, like molecular hydrogen, carbon monoxide, and nitrogen, don't stand a chance. They are instantly, violently torn apart into their constituent atoms and into a soup of highly reactive ions and radicals. This instantaneous destruction, however, is the prelude to a remarkable act of creation. As the immense heat of the discharge dissipates into the surrounding cold gas, a process that happens in mere milliseconds, the environment undergoes a rapid and drastic cooling. The shattered atomic fragments, now mixed together in an extremely dense and excited state, are suddenly forced to find new partners. In this frantic reassembly, the usual rules of slow, cold chemistry are suspended. The sheer density of particles means that statistically unlikely collisions become not just possible but probable. A carbon atom, ripped from its comfortable partnership in a carbon monoxide molecule, might immediately find itself next to a nitrogen atom and several hydrogen atoms. In the chaotic aftermath, they can link up into the backbone of hydrogen cyanide, a molecule that is a veritable Swiss Army knife for prebiotic chemistry. Other fragments might form acetylene, a simple 2-carbon molecule that is a critical stepping stone to more complex hydrocarbons. The discharge acts as a universal blender and a welder, taking the simplest of ingredients and forging them into a rich, new palette of reactive intermediates. What makes this process so compelling is its potential ubiquity and productivity. Astronomers have detected the spectral signatures of a surprising variety of complex organic molecules in the hot cores surrounding young stellar objects, regions so named for their warm, dense gas. Among these are molecules like formaldehyde, methanol, and even vinyl cyanide, a compound that some scientists speculate could form the membranes for hypothetical life in the methane seas of worlds like Titan. While some of this chemistry can be attributed to the gentle warming of ices on dust grains, the sheer abundance and diversity suggest a more energetic formation pathway. Powerful electric discharges provide exactly that, A single, large-scale lightning event in a protostellar envelope could generate a localized explosion of molecular complexity, producing a wide array of compounds in a single, violent pulse. And given the dynamic, chaotic nature of star formation, such discharges are likely not rare events, but a common and recurrent feature throughout the hundreds of thousands of years it takes for a star to accumulate its mass. This theory elegantly bridges the gap between the chemistry of the interstellar medium and that of the protoplanetary disk. The material falling onto a young star system isn't just a pristine, frozen relic. It is being actively processed and upgraded during its very journey inward. The powerful lightning in the envelope acts as a primary refinery, breaking the chemical inertia of the cold cloud and creating a wealth of new, more reactive molecules. When this processed material eventually settles into the flatter, rotating disk where planets will form, it does so already enriched with a sophisticated set of organic building blocks. This means that the chemical inheritance of a planet like Earth may have begun not in the quiet of the disk, but in the electrical storms of its stellar nursery. The raw energy of star birth itself, therefore, might be an essential and universal catalyst, ensuring that new planetary systems are seeded not just with the simple bricks of life, but with a diverse and dynamic toolkit of pre-activated compounds, ready to participate in the next stages of cosmic evolution. While the RNA world hypothesis presents a compelling vision of a single molecule kickstarting life's grand experiment, it does come with its own set of chemical puzzles. The sugar ribose, which forms the backbone of RNA, is notoriously fragile and difficult to form in stable quantities under prebiotic conditions, and the entire RNA molecule itself is vulnerable to breakdown in the very environments where life likely began. This has led scientists to explore a fascinating and elegant alternative. What if RNA was not the pioneer but the successor? What if a simpler, sturdier molecule first held the title of genetic material, a molecule that blended the worlds of proteins and nucleic acids into one hardy hybrid? This is the core premise of the peptide nucleic acid world, a theory that proposes a more robust ancestor for our genetic code. To understand PNA, imagine taking the familiar structure of DNA or RNA and performing a simple but profound molecular swap. In RNA, the backbone is made of alternating sugar and phosphate groups, with the nucleotide bases attached as side chains. PNA replaces that entire sugar-phosphate spine with a backbone constructed from linked units of amino acids, specifically N2-aminethylglycine. This creates a molecule that looks at first glance like a protein chain, but sprouting from that chain are the very same nucleotide bases adenine, guanine, cytosine, and thymine or uracil that form the letters of the genetic alphabet. This fusion of parts results in a molecule with incredible properties. Without the negatively charged phosphate groups, the PNA backbone is neutral. This eliminates the electrostatic repulsion that makes it difficult for two strands of DNA or RNA to approach each other, allowing PNA strands to bind to their complementary partners with a grip that is both stronger and more specific than their natural counterparts. This inherent stability is the theory's greatest strength. The peptide backbone of PNA is far less prone to chemical degradation than the sugar-phosphate backbone of RNA. It doesn't break down easily in water, and it can withstand a wider range of temperatures and pH levels, making it a much more durable candidate for surviving the harsh and variable conditions of the early Earth. Furthermore, the building blocks of PNA are, in theory, more readily available. Its backbone is made from simple amino acids like glycine, which we know were abundant in the primordial soup and have been found in meteorites. The nucleotide bases are the same ones required for RNA, but crucially, PNA does not require the difficult prebiotic synthesis of ribose. It bypasses the messy, non-selective formose reaction entirely, assembling its structure from components that the universe seems to have had an easier time manufacturing. This suggests a more accessible pathway, The first self-replicating system might not have needed to solve the tricky problem of making a robust sugar at all, instead opting for the sturdier and more readily available peptide link. The most compelling evidence for PNA's potential comes from its behavior in the laboratory. PNA oligomers can form remarkably stable double helices with themselves, and they can also readily bind to both DNA and RNA, often with greater affinity than the natural molecules have for each other. This ability to cross-pair is critical. It paints a picture of a potential transitional world where PNA could have been the first genetic polymer, storing information in its base sequence. Later, as the chemical environment evolved and ribose eventually became more abundant, RNA molecules could have formed and begun to replicate, using existing PNA strands as templates. The PNA world wouldn't have needed to be completely displaced in a single revolution. It could have peacefully coexisted and gradually handed over its informational duties to the more versatile, though slightly more fragile RNA, which then went on to dominate due to its superior catalytic abilities. This theory elegantly reframes the origin of life not as a single, miraculous emergence of a perfect molecule, but as a series of evolutionary steps in chemical complexity. The PNA world represents a plausible and robust missing link, a simpler genetic system that could have arisen first, providing a stable platform upon which the more dynamic and catalytic RNA world could eventually be built. It suggests that life's foundation was laid with the most durable and accessible materials available, and that the genetic code we know today is the refined product of a long and patient molecular evolution, beginning with a humble hybrid of peptide and nucleotide that had the resilience to get the entire incredible journey started. Yet, for all the intricate chemistry we've explored in stellar nurseries and on the surfaces of dust grains, some of the universe's most profound molecular factories operate on a scale of almost unimaginable violence. We now turn our attention to the theory of shock synthesis from supernova, the spectacular deaths of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, its core collapses in a fraction of a second, triggering a cataclysmic rebound explosion that blasts the star's outer layers into space at velocities approaching a significant fraction of the speed of light. This is not a gentle dispersal, it is the most energetic regular event in the universe, and for a brief, searing moment, it creates conditions so extreme that they can forge entirely new classes of matter. The supernova's ejector forms an immense, expanding shock wave, a spherical wall of material ramming into the surrounding interstellar gas at millions of miles per hour. Within this propagating front of unimaginable pressure and temperature, a fleeting but incredibly productive chemical forge comes to life. The magic of shock synthesis lies in the sequence of events that follows the initial detonation. As the supersonic shock wave plows into the cold, diffuse gas of the interstellar medium, it doesn't just push it aside, it compresses and heats it instantaneously. The region just behind the shock front becomes an inferno, with temperatures soaring to millions of degrees. In this hellish environment, any pre-existing molecules are instantly and utterly vaporized, torn apart into a plasma of bare atomic nuclei and free electrons. For a moment, it seems like a zone of total destruction, a place where the complex chemistry of the molecular cloud is erased without a trace. But this dissolution is the essential first step. By reducing matter to its most fundamental components, the shock wave creates a perfectly mixed, ultra-dense, and intensely energetic soup of raw ingredients, setting the stage for a phenomenal act of creation as the material rapidly expands and cools. This rapid cooling is the critical phase where complexity emerges from chaos. The expanding debris cloud from a supernova does not stay hot for long. It flies outward at tremendous speed, and as it does, it decompresses and radiates away its immense thermal energy. The temperature plummets from millions of degrees to just a few thousand degrees in a matter of days or weeks, a breathtakingly fast transition on cosmic timescales. It is during this precipitous cool-down that atoms, which were once flying apart with enormous energy, suddenly find themselves in a much denser and cooler environment. They begin to seek out partners, forming bonds in a frantic rush of recombination. Carbon, oxygen, silicon, and iron nuclei start grabbing electrons to become neutral atoms again, and then, almost immediately, those atoms begin linking up. In this dense, cooling gas, three body reactions where two atoms form a molecule and a third atom carries away the excess energy to stabilize it become statistically possible for the first time. This allows for the direct formation of robust diatomic molecules like carbon monoxide and silicon monoxide, which are the building blocks for everything that follows. The most astonishing product of this process, however, is the condensation of dust. As the gas cools further, atoms of carbon and silicon begin to cluster together, nucleating tiny solid particles directly from the vapor phase. Think of it like soot forming in a flame, but on a cosmic and infinitely more violent scale. In the carbon-rich layers ejected from certain types of supernova, carbon atoms link into chains and rings, which then stack and cross-link to form graphite and even diamond nanoparticles. In oxygen-rich environments, silicon and oxygen combine with metals like magnesium and iron to condense into microscopic grains of silicates, the basic stuff of sand and rock. Observations of young supernova remnants with infrared telescopes have confirmed this directly. They detect the warm glow of freshly synthesized dust, proving that these stellar explosions are prolific dust factories. A single supernova can, in one event, seed interstellar space with the equivalent mass of thousands of Earths in new, solid material. But the synthesis doesn't stop at simple dust. The same violent conditions that create these tiny grains are also capable of building complex, carbon-rich molecules right on their surfaces. As the newly formed carbonaceous dust grains are ejected through the still-cooling supernova ejector, they act as flying catalysts. Their surfaces provide a platform where atoms and simple molecules from the gas can adhere and react. The passage through the chemically rich and turbulent debris cloud provides the energy and the raw materials for a final round of molecular assembly. While the full details are still being investigated, it is plausible that precursors to polycyclic aromatic hydrocarbons and even more complex organic compounds could be synthesized in this chaotic environment, their sturdy carbon ring structures allowing them to survive the ongoing turbulence. The supernova, in its death throes, is not just scattering the elements forged in its core. It is actively assembling those elements into the very seeds of future complexity, dust grains and molecules that are far more sophisticated than the atomic gas from which they came. This act of stellar alchemy has profound implications for the chemical evolution of the entire galaxy. The dust and complex molecules manufactured in a supernova are not destined to remain in an isolated cloud. The immense force of the explosion propels them across vast distances, injecting them directly into the interstellar medium. This does two crucial things. First, it enriches the galaxy with heavy elements, the very elements without which planets and life could never exist. Second, and just as importantly, it provides the solid surfaces, the dust grains, that are essential for the more gentle, cold chemistry of molecular clouds to proceed. Without the dust from supernova, the formation of molecular hydrogen via surface catalysis would be vastly less efficient, and the icy mantles that host the formation of sugars and amino acids would never form. In a very real sense, the violent death of massive stars creates the fundamental infrastructure that all subsequent cosmic chemistry relies upon. They are the ultimate recyclers, taking the simple ashes of hydrogen and helium burning and transforming them into the sophisticated, solid-phase materials that will one day become part of new stars, new planets, and perhaps new life. Now, let's travel to a world where the chemistry of life unfolds not in liquid water, but in a freezing river of hydrocarbons under a hazy orange sky. Saturn's largest moon, Titan, offers us a breathtakingly alien laboratory, one where the universe demonstrates its molecular ingenuity under conditions that would be utterly hostile to life as we know it. Here, the average surface temperature is a cryogenic -180 degrees Celsius, cold enough to turn water to stone and to allow methane and ethane to flow as liquids, carving rivers and pooling into great seas. It is within this bizarre and frigid environment that a fascinating chemical pathway unfolds, one that begins with the simplest of carbon molecules and builds towards astonishing complexity, all driven by the faint but persistent energy of the distant sun. This is the acetylene pathway, a cosmic recipe that might be weaving the tapestry of probiotic chemistry on countless cold worlds throughout the galaxy. The entire process starts at the very top of Titan's thick, nitrogen-rich atmosphere. High above the surface, where the haze gives way to the blackness of space, the sun's ultraviolet light penetrates unimpeded. This incoming radiation carries just enough energy to perform a delicate act of chemical surgery. It strikes the most abundant carbon-containing molecule in Titan's atmosphere, which is methane, a simple structure of one carbon atom bonded to 4 hydrogen atoms. The UV photon delivers a precise blow, severing one of the carbon-hydrogen bonds and tearing the methane molecule apart. This creates highly reactive fragments known as methyl radicals, carbon atoms that are missing a partner and are desperate to form new bonds. These radicals don't remain solitary for long. In the dense upper atmosphere, they frequently collide with each other. When 2 methyl radicals meet, they can link up, forming a new molecule with 2 carbon atoms, ethane. But another, more reactive pathway is also available. Some of the methyl radicals can be broken down further, eventually recombining to form a molecule that is far more chemically vibrant: acetylene. Acetylene is the unsung hero of this alien chemical saga. You might know it as the gas used in welding torches here on Earth, where it burns with an intensely hot flame. On Titan, there is no oxygen to burn it, so instead it becomes a fundamental building block. This simple 2-carbon molecule, with its 2 hydrogen atoms and a powerful triple bond between the carbon atoms, is a coiled spring of chemical potential. Its triple bond is rich in energy, making acetylene incredibly eager to react and form more stable, complex structures. As these acetylene molecules drift down through Titan's layered haze, they are exposed to more solar radiation and the energetic particles trapped in Saturn's mighty magnetosphere. This additional energy can excite the acetylene or even break it apart into even more reactive carbon fragments. It is in this energetic, chaotic soup that the first great leap in complexity occurs. The next step involves a kind of molecular cyclization, a process where straight chains of atoms curve around and connect at the ends to form a ring. Under the influence of ultraviolet light, 3 molecules of acetylene can be brought together and induced to link up in a very specific way. They shed some of their hydrogen atoms in the process and form a beautifully symmetrical, 6-sided ring of carbon atoms with a hydrogen atom attached to each carbon. This is benzene, the fundamental unit of all aromatic hydrocarbons and a cornerstone of organic chemistry. The formation of benzene on Titan is a momentous event. It signifies a transition from simple, linear carbon chains to the sturdy, 2-dimensional architecture of rings, a structure that is incredibly stable and serves as a perfect foundation for building ever larger molecular edifices. Once benzene exists in the atmosphere, the pathway to greater complexity accelerates. The same energy sources that created benzene can now act upon it. A photon of UV light can knock one of the hydrogen atoms off the benzene ring, creating a reactive site called a phenyl radical. This radical is like a molecular hand reaching out for another partner. It can readily bond with other hydrocarbon chains and rings drifting in the atmosphere. It might attach to another methyl radical, creating toluene. It could link with a 2-carbon unit to form styrene. Or in an act of molecular stacking, one benzene ring can join with another, creating naphthalene, a two-ringed structure. This process of growth can continue, with rings fusing together into larger and larger sheets of carbon and hydrogen, building up the very same polycyclic aromatic hydrocarbons, or PAH, that we find throughout interstellar space. On Titan, however, they are not just imported curiosities. They are being manufactured locally in vast quantities in the Moon's own skies. The final act of this chemical drama takes place on Titan's surface. All of these complex aromatic molecules synthesized in the upper atmosphere are not destined to remain there. They are too heavy to stay aloft indefinitely. They slowly and continuously drift down through the orange haze, settling out as a fine, reddish-brown organic dust. This is the material that gives Titan its characteristic color, staining the icy landscape and gathering into vast dune fields that stretch across its equatorial regions. But this is not the end of their journey. Titan has an active hydrological cycle, though one based on methane and ethane instead of water. When liquid methane rains from the clouds, it washes this organic dust from the atmosphere and the highlands, concentrating it in the river channels and collecting it in the great lakes and seas of the northern hemisphere. Imagine the shores of Ligeia Mare, a sea of liquid methane and ethane as large as Lake Superior. Here, the complex aromatic hydrocarbons are not just lying inert, they are dissolving and interacting in a cold, non-polar solvent. We do not yet know what long-term chemistry occurs in these alien lakes. It is possible that the dissolved PAHs could slowly stack on top of one another, forming rudimentary layered structures. Or with the immense spans of geologic time available, they could be acting as building blocks for even more complex tholins, the ultimate organic tars that result from Titan's unique atmospheric chemistry. This acetylene pathway, therefore, provides a complete and self-contained system. It starts with the destruction of a simple gas by sunlight and culminates in the deposition of a rich inventory of complex aromatic building blocks into liquid reservoirs on the surface, all without the need for liquid water or Earth-like temperatures. It demonstrates that the universe's drive toward chemical complexity is not bound by our terrestrial assumptions, and that the ingredients for life or for something entirely new and alien may be simmering quietly on worlds we are only just beginning to understand. But while the universe has shown us it can build complexity through specialized pathways, sugars in ices, membranes from lipids, and genetic backbones from clay, there exists an even more elegant and efficient chemical shortcut. This brings us to a theory that centers on a remarkably versatile molecule, one that acts as a veritable Swiss Army knife for prebiotic synthesis. Imagine a single, simple compound that could, under the right conditions, open up to reveal a treasure trove of life's essential building blocks all at once. This is the promise of formamide, a humble molecule composed of just one carbon, one oxygen, one nitrogen, and 3 hydrogen atoms. While its name might sound industrial, its role in the cosmos could be nothing short of foundational, serving as a potential one-pot reactor for forging the very letters of the genetic code, the components of proteins, and the sugars that hold them all together. Formamide's story begins with its surprising abundance in the cold vastness of space. Astronomers have detected its spectral signature in giant molecular clouds, in the swirling disks around young stars, and even on the surfaces of comets and asteroids. It forms readily from the reaction of 2 incredibly common cosmic molecules, hydrogen cyanide and water. Hydrogen cyanide is a staple of interstellar chemistry, a small but highly reactive molecule that is a known precursor to adenine, one of the nucleobases in DNA and RNA. Water, of course, is ubiquitous. Wherever these 2 ingredients meet on the surface of a cosmic dust grain, perhaps energized by a passing ultraviolet photon, they can combine to create formamide. This means the universe appears to be manufacturing and stockpiling this compound on a massive scale, providing a widespread and readily available feedstock for the next stage of chemical evolution. Its presence throughout the galaxy suggests it isn't a rare curiosity, but a fundamental piece of the cosmic chemical inventory, waiting for the right conditions to unlock its potential. The true magic of formamide is revealed when this stored potential is unleashed. On its own, formamide is relatively stable, but when it is exposed to a source of energy or a suitable catalyst, it becomes a chemical powerhouse. In laboratory experiments designed to simulate probiotic conditions, scientists have subjected formamide to a variety of plausible early Earth energy sources, such as ultraviolet radiation, heat, or the shock from an impact event. The results are nothing short of spectacular. From this single starting material, researchers have successfully synthesized all 4 of the nucleobases that make up RNA: adenine, guanine, cytosine, and uracil. These are the fundamental letters of the genetic alphabet, the molecules that store and transmit biological information. To have a single reaction vessel produce the entire set from one common precursor is a staggering chemical economy, a streamlined process that could solve the problem of how these complex information-carrying molecules all came to be present in the same place at the same time. But the generative power of formamide does not stop with the nucleobases. Under slightly different catalytic conditions, this same simple molecule can also yield a variety of amino acids, the building blocks of proteins. It can even be coaxed into producing carbohydrates, including sugars like ribose. This means that formamide represents a remarkable convergence point in probiotic chemistry. Instead of requiring separate, geographically distinct factories, one for nucleobases in a pond, another for amino acids at a hydrothermal vent, and a third for sugars on an asteroid, a great deal of the essential molecular toolkit for life could have been produced simultaneously in a single, concentrated location. A pool of formamide on the early Earth, perhaps collected in a volcanic crater or concentrated on a sun-warmed patch of clay, could have been transformed by a lightning strike or a period of intense solar radiation into a rich, complex broth containing the core components for genetics, metabolism, and structure, all mixed together and ready to interact. The catalysts that facilitate this transformation are as fascinating as the process itself. Certain common minerals like phosphates or various types of clays can dramatically increase the efficiency with which formamide is converted into these biological building blocks. These minerals act as molecular templates, holding the formamide molecules in just the right orientation and providing a surface that lowers the energy required for these transformative reactions to occur. Even more intriguingly, the cosmic radiation that constantly bathes our solar system could have provided the necessary energy input. A deposit of formamide ice on a comet or asteroid, bombarded for eons by cosmic rays, would be continuously processed, its molecules slowly but surely being rearranged into more complex forms. When that comet later impacted a young planet, it would deliver not just the raw formamide, but a pre-made mixture of nucleobases, amino acids, and sugars, effectively jump-starting the planet's chemical evolution with a pre-packaged starter kit of immense sophistication. This formamide-based genesis presents a compelling and beautifully parsimonious vision for life's origins. It suggests that the universe, in its inherent chemistry, has a tendency toward efficiency. Rather than relying on a series of lucky accidents in disconnected environments, it may have favored a unified chemical pathway that could generate multiple classes of biomolecules from a single, abundant cosmic feedstock. The discovery that formamide can serve as this central player profoundly simplifies the narrative of how we came to be, pointing to a cosmos that is not only rich with the ingredients for life, but also pre-programmed with elegant chemical recipes to assemble them. It hints that the leap from inert chemistry to the chemistry of life might be a much shorter, more direct, and more universal step than we ever imagined. To truly appreciate the scale of this cosmic chemistry, we need to shrink our perspective far down to the realm of the microscopic, scattered throughout the immense, dark voids between the stars are trillions upon trillions of the most unassuming, yet most critical chemical platforms in the universe, interstellar dust grains. These are not the dust bunnies you might find under your bed. They are microscopic motes of solid material, primarily silicates and carbon, forged in the violent deaths of ancient stars and scattered across the galaxy like cosmic soot. In the freezing vacuum of a molecular cloud, these tiny grains become something far more significant. They are the universe's most patient and prolific chemical laboratories, and their secret lies in the delicate, icy mantles that slowly accumulate on their surfaces like a gentle cosmic frost. Picture a single one of these dust grains, smaller than a wavelength of visible light, drifting aimlessly through the profound cold and near-total blackness of a giant molecular cloud. The temperature here is only about 10 degrees above absolute zero, a cold so intense that it defies human experience. In this environment, the grain acts like a microscopic magnet for passing atoms and molecules. A water molecule, a carbon monoxide molecule, or a molecule of ammonia, all moving sluggishly in the deep freeze, eventually bumps into the grain. It doesn't bounce off. Instead, it loses what little kinetic energy it has and becomes stuck, frozen in place upon the grain's surface by feeble intermolecular forces known as van der Waals interactions. This process is incredibly slow by our standards, but over the millions of years that a molecular cloud exists, it never stops. Atom by atom, molecule by molecule, a complex, layered mantle of ice builds up around the tiny grain, transforming it from a speck of bare rock into a frozen, multi-layered archive of simple chemicals. This icy coating is not a static shell. It is a dynamic, albeit incredibly slow-moving chemical arena. Even at temperatures near absolute zero, the laws of quantum mechanics grant the atoms and molecules a faint quantum mechanical wiggle. They can slowly, imperceptibly crawl or diffuse across the surface of the ice. This slow-motion migration is the key to everything. It means that two molecules that landed on opposite sides of the grain a million years ago can, through a patient quantum mechanical crawl, eventually find each other. When they finally meet, they don't necessarily have the classical energy to react, but here, the bizarre rules of quantum tunneling we discussed earlier come into play once more. A hydrogen atom can tunnel through the energy barrier to meet an oxygen atom, forming a hydroxyl radical. That hydroxyl radical can then tunnel to meet another hydrogen atom, completing the formation of a stable water molecule, all while frozen solid in the deep, dark cold. This process of accumulation and slow surface diffusion allows for chemistry of surprising sophistication. The icy mantle becomes a layered chemical repository. The first layer to form might be mostly water ice. On top of that, a layer rich in carbon monoxide might accumulate. Then, formaldehyde and methanol might freeze out. These are not inert layers stacked like a sandwich. They are slowly intermingling. A radical created by a cosmic ray strike in the water ice layer can tunnel its way up to the formaldehyde layer, initiating a reaction that begins building a sugar precursor. The mantle, therefore, is not just a storage locker. It is an active, three-dimensional chemical matrix where reactions can occur between molecules that were originally deposited far apart in both space and time. It is a cryogenic assembly line operating on a timescale of millennia, where simple ingredients are methodically linked into more complex organic compounds. The true potential of these icy laboratories is unleashed when the environment around them changes dramatically. When a dense core within the molecular cloud begins to collapse under its own gravity to form a new star, the dust grains trapped within are swept along for the ride. As the protostar ignites and begins to shine, its radiation starts to warm the surrounding material of the protoplanetary disk. For our dust grain, this is a moment of profound transformation. The gentle warmth from the infant star, though still freezing by human standards, is enough to break the weak bonds holding the icy mantle to the grain's surface. The entire frozen matrix, now packed with the complex products of millions of years of cold chemistry, begins to sublimate. The ices don't just melt, they turn directly from solid into gas, puffing away from the grain in a miniature cloud of vapor. In this act of release, the hidden chemical work of the dust grain is finally revealed. The cloud of gas now surrounding the warm grain is no longer the simple mixture of hydrogen, carbon monoxide, and water that originally froze onto it. It is a rich, complex cocktail. It contains the original simple molecules, but now also alcohols, ethers, aldehydes, and perhaps even the simple sugars and amino acids that were painstakingly assembled in the dark and cold. This enriched gas becomes part of the raw material from which the rest of the planetary system will form. The complex molecules are now free to participate in the more energetic chemistry of the protoplanetary disk, or to become incorporated directly into the growing comets, asteroids, and planetesimals that are clumping together nearby. This means that every comet and asteroid that forms in the outer regions of a young solar system is in essence a collection of billions of these spent dust grains and their evaporated mantles, now refrozen into larger bodies. When such a comet later falls into the inner solar system and is warmed by the sun, it reenacts this process on a grand scale, releasing its payload of complex organics into space or depositing them directly onto the surfaces of young planets like Earth through impacts. The icy mantles of interstellar dust grains are therefore the universe's primary method for manufacturing and preserving the chemical precursors to life. They provide a stable, cold, and patient environment where complexity can emerge from simplicity, a slow-motion factory that ensures new worlds are seeded with a rich and diverse chemical inheritance, a direct bequest from the silent, dark clouds that gave them birth. This elegant concept takes us back to the warm, porous structures of alkaline hydrothermal vents, but with a crucial shift in perspective. Instead of focusing solely on the chemical ingredients, this theory highlights the very engine that could have powered their assembly, a fundamental, pre-existing flow of energy. All living cells today, from the simplest bacteria to the neurons in your brain, run on a kind of electrical currency. They actively pump protons, which are simply hydrogen atoms stripped of their electrons across their membranes, creating a difference in concentration, a gradient. It's like charging a battery. When these protons are allowed to flow back across the membrane, down their concentration gradient, they release energy that the cell harnesses to do its most vital work, such as building complex molecules. The stunning proposal of the proton gradient theory is that this sophisticated energy harvesting system wasn't an invention of life, but an inheritance from the non-living geology of the early Earth. The stage for this primordial power plant was the labyrinthine interior of an alkaline hydrothermal vent. These vents are not solid rock, they are complex mineral formations built up from porous materials like iron, sulfur minerals, and green rust. Their structure is filled with a network of microscopic pores and channels, some no wider than a few molecules across. Imagine these tiny compartments as the universe's first natural batteries. On one side of these thin mineral walls, you have the warm, alkaline fluid spewing from the vent itself, rich in dissolved hydrogen gas. On the other side, you have the cooler, more acidic ocean water, rich in carbon dioxide. The mineral wall between them is not a perfect seal. It's a leaky, semi-permeable barrier, and it is precisely this leakiness that creates the power source. The difference in proton concentration between the two sides, the alkaline interior and the slightly acidic exterior, sets up a natural and persistent voltage, a gentle but relentless electrical potential waiting to be tapped. This natural gradient solves one of the most perplexing problems in prebiotic chemistry, the energy cost of building complexity. Many of the reactions that link simple molecules into the long chains essential for life are what chemists call endergonic. They don't happen spontaneously, they require a constant input of energy to force them to go forward. A lightning strike or a burst of ultraviolet light provides a sudden, violent jolt of energy, but it's fleeting and destructive. What was needed was a steady, reliable, and gentle power source, something that could push chemistry uphill over long periods. The proton gradient across the vent walls provided exactly that. It was a geological fuel cell running continuously for thousands, perhaps even millions of years, offering a predictable and durable flow of energy right where it was needed most. So, how exactly was this geochemical energy put to work? The proposed mechanism is beautifully simple and involves the most abundant molecule in the universe, hydrogen. Dissolved hydrogen gas from the vent fluid can passively diffuse through the iron-sulfur mineral walls. As it does, it meets protons that have been pulled from the ocean side, drawn by the electrical potential of the gradient. In the presence of the mineral catalyst, often a form of iron-nickel sulfide similar to the mineral maconite, a remarkable reaction occurs. The hydrogen gas donates its electrons, and with the help of the catalyst, those electrons are used to reduce carbon dioxide. This isn't a random, chaotic process, it's a guided one. The flow of protons essentially acts as a piston, driving this reaction forward and forcing the carbon from carbon dioxide to link up with other atoms. The initial product of this geochemical metabolism is often formate or acetate simple 1 and 2 carbon molecules that are the very entry points into the core metabolic pathways used by all life on Earth today. This process represents a profound continuity between the non-living world and the living one. The first metabolic reactions weren't invented by biology, they were discovered by it. The geochemistry of the vent was already performing a crude version of a core cellular process, chemiosmosis. The vent system provided the membrane, the proton gradient, and the catalyst. All that was needed was for a collection of organic molecules to eventually learn to exploit this free lunch. Over immense spans of time, as these simple organic products became more complex, they could have begun to form their own organic barriers that were better at maintaining the gradient than the leaky mineral walls. They might have evolved primitive molecular machines akin to the protein called ATP synthase found in all modern cells, which acts like a tiny water wheel, capturing the energy of flowing protons to build energy-rich molecules. The transition, then, was not from nothing to something, but from a geologically driven chemical system to a biologically driven one that learned to internalize and control the very energy source that gave it birth. This theory's power lies in its ability to answer the "why here?" question with resounding clarity. The deep-sea vent environment was not just a random place where chemicals happened to be concentrated. It was one of the few places on the early Earth that provided the entire package. A constant source of simple reactants like hydrogen and carbon dioxide, powerful mineral catalysts, protective microcompartments, and most importantly, a continuous, renewable, and controllable energy source that was physically structured across a barrier. It turns the origin of life from a story of random chemical collisions in a soup into a narrative of energy-driven organization within a structured habitat. If this theory is correct, it suggests that life is not a bizarre fluke, but a likely outcome of planetary geochemistry wherever a rocky, water-rich world possesses the right kind of internal heat and chemistry, offering a deeply optimistic view of life's potential wherever similar vents might exist on the frozen ocean floors of moons like Europa or Enceladus. So we've seen how polarized starlight and mineral surfaces could have tipped the scales toward life's one-handedness. But there is another, far more fundamental cosmic force that might have written this preference directly into the universe's operating code. This idea takes us beyond chemistry and into the subatomic realm, suggesting that the very faintest force in nature, the weak nuclear force, acting within the vast magnetized clouds of star-forming nebulae, could have been the ultimate architect of biological homochirality. It's a theory that connects the asymmetry of life directly to an asymmetry woven into the fabric of the cosmos itself. To grasp this, we need to understand a subtle but profound property of the weak force. Of the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, the weak force is unique because it violates what physicists call parity symmetry. In simple terms, parity symmetry means that the laws of physics should work the same way for an object as they do for its mirror image. Imagine filming a physics experiment and then watching the film in a mirror. If parity holds, both the real event and its mirror reflection should be equally possible according to the laws of physics. But in the 1950s, physicists Qin-Xiong Wu and others discovered that for interactions governed by the weak force, this is not true. The weak force has an inherent handedness. It treats left-handed and right-handed particles differently. This means the universe, at its most fundamental level, is not completely ambidextrous. It has a slight built-in bias. The great challenge, however, was translating this tiny subatomic bias into the macroscopic chemical world of molecules. The weak force's influence is incredibly feeble, vastly overpowered by the electromagnetic forces that govern chemistry. How could such a subtle effect ever be amplified enough to affect the formation of a sugar or an amino acid? The proposed solution involves a two-step cosmic amplification process, beginning with the vast, dynamic environment of a protoplanetary nebula. These swirling clouds of gas and dust from which solar systems are born are not featureless blobs. They are often permeated by large-scale magnetic fields, generated by the motion of ionized gas within them. These magnetic fields can have a profound ordering effect on the tiny dust grains and the molecules forming on them. As these particles drift through the cloud, they can become aligned with the magnetic field lines, much like iron filings arranging themselves around a bar magnet. For chiral molecules, which are often asymmetrical and can spin in specific ways, this alignment is crucial. It means that the entire nebula can, in a sense, become a coordinated system, with countless trillions of molecules all oriented in a similar way relative to the magnetic field, rather than pointing in random directions. Now enter the weak force, when high-energy electrons produced by radioactive decay within the nebula or by cosmic rays come flying through this magnetically organized cloud. They interact with these aligned molecules. Due to parity violation, the weak force causes these electrons to interact very slightly more with one chiral form of a molecule than with its mirror image. It's an almost imperceptible difference, a fraction of a percent. But in the context of a giant molecular cloud containing an almost unimaginable number of molecules and over millions of years, this tiny preference can be statistically amplified. Think of it like a vast cosmic election with trillions of voters, where one candidate wins by just a handful of votes. The margin is razor thin, but the outcome is decisive. The magnetized nebula acts as the organized polling station, ensuring the vote is fair and coordinated, while the weak force provides the minuscule, consistent nudge that breaks the tie. This process wouldn't create pure homochirality instantly. Instead, it would establish a very small but persistent excess of one-handedness throughout the entire nebula. This initial bias, imprinted into the raw material of the solar system before any planets formed, is then preserved and further amplified by the very processes we've discussed before. The slightly biased molecules become incorporated into asteroids and comets. On their surfaces, the preferential destruction of one form by polarized light from nearby stellar explosions could work in concert with this initial weak force bias rather than against it, strengthening the signal. Then, when these materials are delivered to a young planet like Earth, chemical processes like autocatalysis take over, a self-replicating system that stumbles upon the slightly more abundant left-handed amino acids, for example, would quickly snowball, consuming that form and overwhelmingly producing more of it, while the minority-handedness is left behind as unused scraps. The weak force provided the first faint whisper of a preference, and chemical evolution did the rest. shouting that preference from the molecular mountaintops until it became the universal rule of biology. What makes this theory so compelling is its profound universality. The weak nuclear force is a fundamental constant of the universe, and magnetic fields are a common feature of star-forming regions. If this mechanism is correct, then the initial chiral bias for life may not be a random local accident, but a standard feature of planetary formation across the galaxy. Every solar system that forms within a magnetized nebula could potentially inherit the same initial handedness preference. This might mean that if life exists elsewhere, its proteins could also be built from left-handed amino acids and its nucleic acids from right-handed sugars, not because of a shared ancestor, but because the same fundamental physical law guided its chemical dawn. It suggests that the one-handedness of life is not a quirky detail of our own biology, but a direct signature of a deeper cosmic asymmetry, a testament to the fact that we are not just living in the universe, but are truly and intimately woven from its most fundamental and lopsided threads. While we've spent our journey marveling at the universe's intricate carbon-based chemistry, from the sugars in molecular clouds to the self-replicating potential of RNA, we must also consider a truly alien possibility. What if the path to complexity we know and are made of is merely one of many? What if, under conditions so extreme they dwarf our terrestrial experience, the universe experimented with a completely different kind of chemistry, building complexity not from carbon, but from the very rocks and sand that form the bones of planets? This is the provocative, fringe idea known as the silicate world hypothesis, a theory that dares to imagine a biology not of carbon but of silicon. To understand this radical departure, we need to appreciate the chemical cousinhood of carbon and silicon. In the periodic table, silicon sits directly beneath carbon, meaning they share a similar outer electron shell structure, which dictates how they bond with other atoms. This similarity is why carbon is so versatile. It can form 4 strong, stable bonds, creating long chains and complex rings that serve as the scaffolding for life. Silicon can also form 4 bonds, and in fact, it is one of the most abundant elements in the Earth's crust. We are surrounded by its handiwork. The vast deserts of sand, the bulk of rocks and clay, are all made of silicates compounds of silicon and oxygen. But there's a crucial difference that has long made scientists skeptical of silicon-based life. When carbon reacts with oxygen, it forms carbon dioxide, a gas that is easily exchanged in the atmosphere and oceans. When silicon reacts with oxygen, it forms silicon dioxide quartz and sand, a solid that is notoriously inert and crystalline at the temperatures we find comfortable. It seems to lack the dynamic, fluid chemistry necessary for life. The silicate world hypothesis, however, argues that we are looking at silicon in the wrong environment. Our entire frame of reference is based on a narrow window of temperature and pressure, the conditions on the surface of a temperate, water-rich planet. But the universe is filled with far more extreme locales. Imagine the surface of a young, molten planet, freshly coalesced from the debris of the protoplanetary disk. Here, temperatures could soar to many hundreds or even thousands of degrees Celsius. In such a furnace, the rules of chemistry are rewritten. The solid, rigid silicate minerals we know would be liquefied into a seething magma ocean. In this molten state, freed from the rigid crystalline lattices of solid rock, silicon atoms could gain a new kind of mobility and flexibility. Under these high-temperature, high-pressure conditions, it's theoretically possible for silicon to begin forming polymers long, chain-like molecules analogous to the hydrocarbons that form the backbone of our organic chemistry. These silicate chains could, in principle, branch and fold, creating a diversity of structures that might serve as the basis for a very different kind of metabolic or replicative system. The potential environments for such chemistry are as breathtaking as they are hostile. Beyond the surfaces of lava worlds, consider the atmospheres of cool, carbon-rich stars. In these stellar furnaces, astronomers have detected the spectral signatures of molecules like silicon carbide, suggesting that silicon is actively participating in a complex gas phase chemistry. Within the turbulent, high-energy plasma of these stellar atmospheres, with temperatures and pressures that make a molten planet seem mild, the formation of transient, complex silicate polymers is not beyond the realm of physical possibility. Furthermore, the immense pressures deep within the mantle of a large rocky planet could force silicates into exotic, non-crystalline forms, creating a dense, slow-moving medium where silicon-based chemistry could unfold over geological timescales, utterly isolated from the world of carbon and water above. Yet, for all its imaginative appeal, the silicate path faces monumental challenges that explain why it remains a fringe theory. The primary obstacle is the profound stability of silicon-oxygen bonds and the resulting solid state of its oxides. A silicon-based biology would need a solvent very different from water, one capable of dissolving silicate networks to allow for dynamic chemical exchange. On a scorching world, perhaps a sea of molten sulfur or liquid metal could serve this purpose, but such solvents are far less versatile than water. Even more critically, the very bonds that give silicon its potential also limit its versatility. Silicon-silicon bonds are significantly weaker than carbon-carbon bonds, making long chains much less stable. They are prone to reacting with oxygen and locking up into rigid, glassy, or sandy minerals, effectively ending any prospect of complex, evolving chemistry. This inherent instability suggests that while a silicate world might momentarily flicker with complexity, it would be a fleeting phenomenon, quickly snuffed out as the system cools and solidifies into a permanent crystalline tomb. Ultimately, the silicate world hypothesis serves not as a proven pathway, but as a crucial thought experiment that expands our definition of life itself. It forces us to confront our carbon-based chauvinism and recognize that the principles of life, a system that harvests energy, maintains complexity, and replicates, might be universal even if the chemical implementation is not. While carbon, with its unparalleled talent for forming stable yet dynamic bonds in a watery medium, appears to be the clear winner in the cosmic competition for complexity, the universe is a place of infinite variety. The fleeting existence of complex silicate polymers in the hellish forge of a young planet or a stellar atmosphere reminds us that the story of chemistry is vast and that our own existence is a testament to one particularly successful and stable formula, but perhaps not the only one that was ever attempted in the grand, turbulent laboratory of the cosmos. But perhaps one of the most dynamic and enduring environments for this cosmic chemistry isn't found drifting in the void or simmering on the seafloor of a young Earth, but locked in a perpetual gravitational dance around a giant planet. This brings us to the icy ocean worlds of our own outer solar system, moons like Jupiter's Europa and Saturn's Enceladus. These seemingly frozen orbs, sheathed in crusts of water ice, hide a profound secret beneath their surfaces: vast, global, liquid water oceans. For such oceans to remain unfrozen in the profound cold of deep space, they require a powerful and continuous source of internal heat. That heat doesn't come from the distant sun, but from a relentless cosmic tug of war, the immense tidal forces exerted by their colossal parent planets. This constant gravitational flexing transforms these icy moons into some of the most promising and long-lived natural laboratories for prebiotic chemistry in our entire solar system. To understand this process, you first have to visualize the orbital dynamics at play. A moon like Europa doesn't orbit Jupiter in a perfect circle. Its path is slightly elliptical. This means its distance from the giant planet is constantly changing. As Europa swings closer to Jupiter, the planet's immense gravity pulls harder on the near side of the moon than the far side, stretching it slightly. Then, as the moon swings farther away in its orbit, that gravitational grip relaxes, and the moon settles back into a more spherical shape. This isn't a single dramatic event. It's a continuous rhythmic pulsing, a flexing of the entire moon's structure with every single orbit. For Europa, this cycle repeats every 3.5 Earth days, and it has been doing so for billions of years. This perpetual kneading, much like repeatedly bending a metal coat hanger back and forth, generates an immense amount of internal friction and heat through a process known as tidal dissipation. It is this frictional warmth, generated deep within the moon's rocky mantle, that is powerful enough to melt a layer of ice from below, creating and sustaining a globe-spanning ocean trapped between a frozen surface and a rocky seafloor. This creates an environment with stunning parallels to the hydrothermal vent systems we believe were so crucial on the early Earth. On our planet, the heat-driving seafloor vents comes from the radioactive decay of elements in Earth's core and the residual heat from our planet's formation. On Europa and Enceladus, tidal heating provides that same essential service. Scientists are confident that the rocky beds of these subsurface oceans are geologically active, heated by this tidal energy. This means that on the seafloor of Europa, there are almost certainly hydrothermal vent systems, cracks and chimneys where mineral-rich, superheated water from the moon's interior gushes out into the cold, dark ocean above. These are not just theoretical. The plumes of water vapor and ice crystals erupting from fissures in the south pole of Enceladus, sampled directly by the Cassini spacecraft, contain tiny grains of silica nanograins. The specific size and composition of these silica particles are a telltale chemical signature that they could only have formed in water that was in contact with rock at temperatures of at least 90 degrees Celsius, providing compelling indirect evidence for ongoing hydrothermal activity on the seafloor far below the ice. What makes these tidally heated oceans such compelling crucibles for chemistry is their sheer longevity and stability. While the surface of a young Earth was a violent and chaotic place, bombarded by asteroids and blasted by ultraviolet radiation, the ocean of Europa has been a protected, dark, and thermally stable environment, possibly for the entire history of the solar system. The icy crust, which may be dozens of kilometers thick, acts as a perfect shield protecting the ocean beneath from radiation, asteroid impacts, and the vacuum of space. Within this submerged world, the essential ingredients for life are all present and have been mixing for eons. The water itself is the universal solvent. The rocky seafloor provides a source of minerals and potential catalysts, like the iron-sulfur minerals so crucial to the metabolism-first theories, and the continuous energy flow from the hydrothermal vents provides the persistent, gentle power needed to drive endergonic reactions, pushing chemistry uphill toward complexity, just as the proton gradient theory suggests. This combination of stability and energy creates a chemical environment that could be even more favorable for the rise of complexity than the early Earth's oceans in one crucial way: time. On Earth, the window between the end of the heavy bombardment and the earliest evidence of life was perhaps only a few 100 million years, a relatively short span for such a momentous transition. In contrast, the subsurface ocean of Europa has likely existed in a stable, liquid state for over 4 billion years. This offers an almost unimaginably long, uninterrupted duration for chemical networks to establish themselves, for molecular chains to grow, and for simple systems to stumble upon the principles of replication and evolution. It's the difference between trying to write a symphony in a single afternoon versus having a lifetime to compose, refine, and orchestrate it. The constant, rhythmic input of tidal energy ensures this creative process is never shut down by a lack of power, making these hidden oceans the ultimate long-term experiment in prebiotic chemistry, an experiment that has been running in slow motion since the dawn of our solar system. The implications of this theory extend far beyond our own celestial backyard. If tidal heating can create and maintain habitable conditions on moons orbiting gas giants, then the number of potential abodes for life in our galaxy skyrockets. Jupiter-like planets are common around other stars, and many of them will likely have their own families of icy moons. A gas giant located within its star's habitable zone, the region where temperatures are just right for liquid water on a planet's surface, isn't even necessary. The habitable zone for life becomes not a belt around a star, but a condition created by the gravitational relationship between a moon and its planet. A frozen moon orbiting a gas giant far from its star's warmth could still host a thriving, living ocean deep beneath its ice, powered entirely by tidal forces. This radically expands the real estate for biology in the cosmos, suggesting that lifeless, frozen worlds might be the exception, not the rule, and that the most common form of life in the universe may not dwell on a planet's surface basking in sunlight, but in the perpetual, radiant darkness of a subsurface sea, warmed from within by the eternal, gravitational embrace of a giant. Yet this grand story of cosmic chemistry is not confined to our own solar system. As we cast our gaze outward to the thousands of strange and wonderful worlds now known to orbit distant stars, we find that the universe's molecular factories may operate on scales and in environments that dwarf even our most imaginative terrestrial examples. Picture a gas giant not unlike Jupiter, but orbiting perilously close to its parent star, a world known as a hot Jupiter. Its atmosphere, perpetually scorched by stellar radiation, is a churning, turbulent cauldron of exotic gases, whipped by supersonic winds into a permanent and planet-wide storm. Here, the raw ingredients for probiotic chemistry are not frozen on dust grains but are boiling in a vast, gaseous sea. And the energy source is not a gentle geothermal heat, but the relentless, brutal fury of the star itself. The upper atmospheres of such worlds are bathed in an intense, unending shower of ultraviolet radiation, which acts like a colossal and continuous version of the Miller-Urey experiment, but on a planetary scale. This high-energy light relentlessly breaks apart stable molecules like methane and ammonia, creating a thick soup of reactive radicals that are then mixed deep into the hotter, lower atmospheric layers by the planet's violent weather systems. In these warmer, denser regions, these fragments can collide and reassemble into chains and rings, potentially creating a rich haze of complex organic molecules that could envelop the entire planet. This isn't a slow, patient process in a dark cloud. It is a frantic, high-energy assembly line running non-stop in the sky of an alien world, suggesting that some of the most prolific organic factories in the galaxy might not be planets like Earth at all, but these hellish, gaseous giants. Venturing even further into the realm of the exotic, we encounter a class of worlds that turn our understanding of planetary chemistry on its head: carbon planets. While Earth is built primarily from silicates and oxygen, a carbon planet would form in a region of space that was exceptionally rich in carbon, perhaps around a star that itself contained an overabundance of this element. On such a world, the very geology would be alien. Imagine mountains of graphite, valleys paved with layers of diamond, and tar-like seas of complex hydrocarbons. The atmosphere of a carbon planet could be a thick, smoggy shroud rich in gases like carbon monoxide, methane, and acetylene. In this environment, the pathways to complexity we see on Titan would be amplified to a staggering degree. The constant stellar energy input would drive the chemistry of acetylene and methane toward ever more complex aromatic structures, potentially creating a permanent, global drizzle of organic tholins far more diverse and abundant than anything in our solar system. The surface of such a world might be covered in a bitumen-like substance, a tarry matrix within which novel forms of chemical complexity could stew for billions of years. Without water to dissolve and dilute them, these organics would interact in ways we can scarcely model, using liquid hydrocarbons or even supercritical carbon dioxide as their solvent. The molecules forged in this carbon-saturated environment could be entirely different from the water-based chemistry we know, leading to forms of prebiotic complexity that are truly alien, demonstrating that the universe's recipe book for organic molecules is far thicker and more varied than the single chapter we have explored on our own world. What makes these exoplanetary atmospheres such compelling crucibles is the sheer diversity of energy sources available to drive reactions. Beyond the dominant stellar ultraviolet light, many of these worlds possess significant internal heat left over from their formation, which can drive convection that cycles atmospheric gases from the cold, stable upper layers down into searing hot high-pressure depths and back up again. This creates a continuous thermal cycling, much like a planetary-sized reflux condenser in a chemistry lab, repeatedly subjecting molecules to a range of temperatures and pressures that can promote different stages of synthesis. Furthermore, the immense electrical activity within the cloud systems of gas giants, with lightning strikes thousands of times more powerful than those on Earth, could provide colossal, sporadic jolts of energy, shattering simple molecules and forcing the recombination of their fragments into more complex forms in a process akin to the shock synthesis we see in protostellar envelopes. This combination of constant UV photochemistry, thermal cycling, and catastrophic electrical discharges presents a multi-pronged assault on molecular simplicity, suggesting that the atmospheric soups of these distant worlds could be brewing a menagerie of complex organics that we have not yet even conceived of in our laboratories. The ultimate testament to this potential lies in the data we are already gathering. When a distant exoplanet transits or passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. By analyzing this filtered starlight with powerful instruments like the James Webb Space Telescope, astronomers can decode its spectral signature, identifying the fingerprints of specific molecules present in that alien sky. We have already detected water vapor, sodium, and carbon dioxide in the atmospheres of hot Jupiters. More recently, and more tantalizingly, there have been tentative detections of more complex molecules, including potential signatures of benzene and other hydrocarbons. Each new spectral line is a cipher, a piece of a puzzle that points toward the chemical activity brewing in that distant environment. As our telescopes grow more powerful, we will undoubtedly find clearer evidence of even larger organic molecules. The goal is to one day identify a true biosignature, a molecule or combination of molecules that is almost certainly a product of life, like the oxygen-methane disequilibrium we see on Earth. But to confidently recognize such a signature, we must first understand the full, rich canvas of non-biological, prebiotic chemistry that the universe is capable of painting on its own. The complex organics in exoplanet atmospheres are the background against which the signal of life must be distinguished, and by studying these planetary-scale laboratories, we are essentially learning to read the universe's own chemical language, a language written in the swirling clouds of worlds far beyond our own. But to truly push the boundaries of our cosmic imagination, we must journey back to the very beginning of everything, to a time when the universe was not cold and dark, but an unimaginably dense and brilliant fireball, still ringing with the echoes of its own creation. This brings us to our final and perhaps most profound theory, the idea that the very afterglow of the Big Bang itself served as the universe's first and most universal energy source, providing the photons needed to ignite the initial sparks of molecular complexity. We are talking about the cosmic microwave background radiation, but not as we observe it today, a faint, cold whisper in the void, but as it existed in the universe's fiery youth, a blazing, all-pervasive light that filled every corner of existence and could have acted as a primordial reactant, driving the very first chemical experiments in the cosmos. Today, the cosmic microwave background is a cold relic. After traveling for over 13 billion years through an ever-expanding cosmos, the light from the Big Bang's aftermath has been stretched and cooled, its photons now possessing energy equivalent to a temperature of just 2.7 degrees above absolute zero. It is a fossil, a snapshot of the universe when it was a mere 380,000 years old. But to understand its potential role in early chemistry, we must rewind the cosmic clock. Go back further to a time just a few million years after the Big Bang. The universe is still hot, dense, and opaque, a seething plasma of electrons and nuclei. When it finally cools enough for these particles to combine into stable atoms, primarily hydrogen and helium, the universe suddenly becomes transparent. For the first time, light can travel freely, and in that moment, the universe is flooded with an intense, brilliant light, a radiation field with a temperature not of 3 degrees, but of thousands of degrees hotter than the surface of a red dwarf star. This was the cosmic microwave background in its prime, not a faint microwave hum, but a searing bath of optical and ultraviolet photons permeating all of space. This universal light bath would have been the most powerful and consistent energy source in the entire early cosmos. Before the first stars flickered to life, before the first supernova scattered their heavy elements, this was the only game in town. Any atom or molecule that formed would have been instantly bathed in this intense radiation. At first glance, this seems like a purely destructive force. High-energy photons are excellent at breaking molecules apart, a process known as photodissociation. And indeed, in the earliest epochs, this radiation would have made it very difficult for anything more complex than single atoms or the most robust diatomic molecules to survive for long. But destruction and creation are two sides of the same chemical coin. This relentless radiation could also provide the precise, energetic nudge needed to push simple systems over an energy barrier, allowing them to form the first fragile bonds. It's the same principle as the photochemistry we see in protoplanetary disks, but operating on a universal, foundational scale. The most likely candidate for this first, tentative step is the formation of the molecular hydrogen ion known as H2+. This is not the stable H2 molecule we know, but a more reactive, positively charged version. The process would have begun with the universe's most abundant resource, neutral hydrogen atoms. A hydrogen atom consists of a proton and an electron. When one of these atoms was struck by a high-energy photon from the early cosmic microwave background, the photon could deliver a powerful kick, ripping the electron away and creating a bare proton and a free electron in a process called photoionization. These free particles would then zip through the primordial gas. Crucially, a free proton could sometimes collide with a neutral hydrogen atom. In this dense, early environment, such a collision could result in the formation of the H2+ molecular ion, where the two protons share a single electron in a fragile but real chemical bond. This molecule is not very stable, but its mere existence would have been a monumental achievement. The universe's first covalent bond, forged directly by the energy of its own creation. This simple molecular ion would have been a crucial catalyst for the next, even more important step, the formation of neutral molecular hydrogen, H2. The H2+ ion, once formed, is highly reactive. It can easily attract the free electrons that are zipping through the primordial gas. When an electron collides with an H2+ ion, it can be captured, causing the ion to dissociate into two separate hydrogen atoms. However, in a small but significant number of collisions, the electron's energy can be carried away by another particle or a photon, allowing the system to settle into a stable, neutral H2 molecule. This pathway, known as the H2+ pathway, provides a much more efficient route to forming the universe's primary molecular fuel than the slow process of two atoms meeting on a dust grain. Especially since in this very early era, dust grains did not even exist yet. The cosmic microwave background, therefore, may have provided the essential kickstart, creating the reactive intermediates that allowed the first true molecules to assemble, seeding the cosmos with the hydrogen gas that would later collapse to form the very first stars and galaxies. The implications of this are staggering to consider. It suggests that the universe did not wait for stars to ignite before it began its chemical evolution. The very conditions of the early cosmos, its density, its temperature, and the pervasive energy of its own background radiation, were sufficient to initiate a rudimentary but vital chemistry. This process would have been most efficient in the slightly denser regions of the universe, the protogalactic clouds that were the precursors to the first galaxies. Within these clouds, the first molecules of H2 would have begun to form, and molecular hydrogen is a vastly more efficient coolant than atomic hydrogen. As these molecules radiated energy away, they allowed the dense clouds to cool and contract further, accelerating the gravitational collapse that led to the birth of the first stellar populations. In this view, the cosmic microwave background wasn't just a passive relic. It was an active participant in the universe's development, its photons acting as a cosmic match, striking against the flint of primordial hydrogen to spark the faintest glow of molecular life, a glow that would eventually grow into the brilliant fire of the first stars, illuminating the dark and setting the stage for the complex chemistry that was yet to come. From the deep-sea vents where proton gradients powered the first metabolic reactions to the frigid interstellar clouds where quantum tunneling quietly assembled sugars on grains of cosmic dust, the story of our universe's first complex molecules is not a single linear narrative. It is a breathtaking tapestry woven from countless threads, a symphony of chemical creativity playing out across every conceivable environment. We have journeyed through the chaotic atmospheres of distant exoplanets, witnessed the formation of robust carbon cages around dying stars, and even peered back to the universe's fiery infancy, where the afterglow of creation itself may have sparked the very first molecular bonds. This incredible diversity of theories reveals a profound truth. The cosmos is not a barren void, but a vast, interconnected network of chemical laboratories, each with its own unique tools, energy sources, and pathways toward complexity. The journey from a cloud of simple atoms to the intricate chemistry of life appears not as a single, improbable road, but as a galactic superhighway with countless on-ramps and merging lanes. What becomes overwhelmingly clear is that the universe seems to possess a fundamental, built-in bias for building complexity from simplicity. Whether through the gentle, persistent chemistry on a dust grain, the violent shock of a supernova, or the structured energy flow across a mineral membrane, the same outcome emerges time and again. The essential building blocks of life, amino acids, sugars, nucleobases, and the membranes to contain them arise not as miraculous accidents, but as natural, even probable, consequences of physics and chemistry under a wide range of conditions. This suggests that the emergence of life is not a fluke unique to our pale blue dot, but a deeply ingrained potential of the cosmos itself, a process that may be unfolding right now in the subsurface ocean of Europa, in the hydrocarbon lakes of Titan, or in the hazy skies of a distant hot Jupiter. Each theory we have explored, from the elegant simplicity of the formamide pathway to the sophisticated logic of the RNA world, is a vital piece of this grand puzzle, offering a different perspective on how non-living matter can cross that profound threshold into the realm of biology. Ultimately, this quest to understand the universe's first molecules is a quest to understand our own deepest ancestry. The carbon in our cells, the oxygen in our lungs, and the intricate molecules that orchestrate our every function were forged in the hearts of long-dead stars and assembled in the dark, cold nurseries between them. We are not merely living in the universe, we are the universe, a way for the cosmos to become conscious of itself. The chemical pathways that led to us are written into the fabric of reality, and by unraveling them, we are reading our own cosmic birth certificate. So, as we conclude this journey through 30 of the most compelling theories, we turn the question over to you. Which of these cosmic origin stories resonates most deeply with you? Is it the protected, energy-rich world of hydrothermal vents, the patient, cold chemistry of interstellar clouds, or the revolutionary potential of a self-replicating RNA molecule? Let us know in the comments below, and don't forget to subscribe for more journeys into the